Hello, and welcome to Sleepy Science. I am so glad you are here. Whether your mind is restless, your eyes are heavy, or you just enjoy falling asleep to the gentle rhythm of wonder. Tonight, we'll quietly explore the senses, those invisible bridges between you and the world around you. But what if those senses were hiding secrets? What if your nose never truly stopped smelling? Your skin could detect light, or your ears could pick up motion itself. From emotional echoes in a single touch to the strange connection between sound and taste. This episode is a soft journey through the overlooked miracles of your own body. Nothing loud, nothing rushed. Just you, your breath, and the quiet science of how you experience reality. Before we begin, I'd love to know, where in the world are you listening from? And what time is it there? Are you winding down beneath city lights, or listening in the still glow of night? If this kind of peaceful exploration helps you sleep, or simply helps you feel, please consider liking and subscribing. It means the world to me, and helps more sleepy scientists find their way here. Now, take a slow breath, settle in, and let's begin our gentle walk through the hidden truths of your senses. You can smell emotion. You're walking down a hallway and someone passes by. They don't speak. They don't look at you, they don't touch you, and yet something inside you shifts, like the air itself has whispered a secret. You suddenly feel tension or sadness or warmth, and you have no idea why, but your instincts flare before your mind catches up. What if I told you that what you felt wasn't imagined, but inhaled, that emotions aren't just seen or heard, but smelled, silently carried in the air like invisible signals? Your body decodes without permission, without even telling you it's doing it. This isn't a poetic metaphor. It's neurobiology in action. Human beings, like many other animals, constantly emit subtle chemical compounds through sweat, breath, and skin. And some of those compounds, especially in moments of intense emotional arousal like fear, anger, or joy, carry specific molecular markers. When someone's afraid, their body doesn't just tremble, it produces different kinds of sweat. And inside that sweat are tiny molecules, chemosignals, that your nose picks up, even if you never consciously notice the smell. Scientists have exposed people to sweat collected from terrified individuals and recorded measurable physiological changes. Their hearts beat faster, their amygdala, the brain's fear center, lights up, and they start scanning their environment more cautiously, all without ever being told what they were inhaling. What this means is startling. Your nose isn't just passively filtering scents, it's receiving silent emotional broadcasts from other humans, tuning into frequencies of feeling embedded in biology, bypassing language, context, and even awareness. And it goes deeper, because unlike sight or hearing, the olfactory system is directly wired to the limbic brain, which is the seat of memory and emotion. Most other senses pass through the thalamus, a kind of relay hub before reaching the brain's higher areas. But smell is primal. It takes a shortcut. That's why scents can jolt you into memories without warning. The smell of someone's coat might make you feel safe, or a whiff of something on a subway platform can drown you in grief from a moment years ago. But emotions don't just come with smells. They are smells, in a way. Fear sweat smells different from workout sweat. Grief sweat differs from joy sweat. Even happiness has a traceable scent profile, though less studied. In one remarkable experiment, volunteers wore absorbent pads under their arms while watching horror films or comedies, and their sweat was then stored and later presented, without explanation, to new participants. The people who sniffed the fear sweat showed increased vigilance and anxiety, while those exposed to the happy sweat smiled more often and interpreted neutral faces as more friendly. And again, none of them knew they were reacting to someone else's emotions. It was all happening below awareness, which leads to a profound question. How much of your own emotional state, your sense of safety or discomfort, is actually yours? And how much is chemically absorbed from people around you? This challenges the way we think about human connection. We often assume we know what others are feeling because we read their expressions or interpret their tone of voice. But what if your brain has already decided how to feel about someone before your conscious mind has even formed a thought, based solely on the emotional molecules they're releasing into the air? Think about that the next time you enter a room and feel weird. Maybe you're not imagining it. Maybe someone's grief is hanging in the molecules around you, whispering its shape to your nervous system. Or maybe you feel drawn to someone not because of what they say, but because your brain recognizes their scent as emotionally congruent with your own. This opens the door to a strange kind of empathy, not intellectual, not even visual, but molecular. Smell becomes a medium for emotional resonance, like an invisible language the body speaks in particles instead of words. And while we've long accepted that dogs can sense fear, or that animals react to hormonal changes in their group, we've been reluctant to acknowledge the same capacity in ourselves. But the science is clear. Humans are chemosensory creatures. Our noses don't just pick out perfume or smoke. They pick up unspoken emotion. What's especially fascinating is how this sensitivity starts early. Even newborns respond to their mother's scent in ways that affect their emotional regulation. Infants can distinguish between the scent of maternal stress and calm, and their own physiology adapts accordingly, meaning that long before a child understands the concept of emotion, they are already absorbing it through their nose. And as we grow, that system becomes more complex, but never shuts off. It becomes background noise, unless you start to notice. Some researchers have even found that people can detect emotional states through smell with surprising accuracy, even in modern urban environments full of competing odors. You may not identify a specific scent as fear, but your body might nonetheless change posture, modulate voice, or experience a flash of anxiety, all triggered by invisible emotional data. But what does this mean for how we live, for how we build relationships, conduct therapy, or even design environments? It suggests that every shared space is also a shared emotional field, not just psychologically, but physically. That workplaces filled with fear or stress may literally circulate molecules of anxiety that prime everyone for tension. That therapy rooms, classrooms, even public transit are not emotionally neutral zones. There's potential here for everything from scent-based interventions to early warning systems for emotional health. Imagine being able to detect group emotional shifts before anyone speaks a word. Not by facial recognition, but by the chemical atmosphere in the room. It also raises ethical questions. If emotion can be detected and even transmitted chemically, can it be manipulated? Could spaces be engineered to emit calming or joyful chemosignals? And should they? And then, beyond the lab and the clinic, there's the philosophical weight of this discovery. We like to think of ourselves as self-contained, that our feelings begin and end within the borders of our skin. But the truth may be much more porous. You are not just a single emotional entity. You are a porous membrane, constantly exchanging feeling with the world around you. Some of your sadness may be borrowed. Some of your joy may be echoed. You are breathing in other people's hearts, and they are breathing in yours. In this light, compassion becomes not just a moral stance, but a biological reality. To care for others is to care for yourself, because the emotional air you cultivate in your home, your work, your daily presence, will eventually find its way back into your own lungs. And perhaps that's the soft, lingering truth at the center of this topic, that even in a world fractured by language, difference, and misunderstanding, we are still speaking to each other, through breath, through skin, through molecules shaped by how we feel. Every sigh you exhale is a kind of message. Every crowded train is a kind of chorus. We may not always hear each other clearly with words, but your body is always listening, and so is everyone else's. You are not isolated in your emotion. You are surrounded by an invisible network of shared feeling, breathed in and out with every heartbeat, exchanged in silence, but never without meaning. You have more than 5 senses. You were probably taught, somewhere between early school books and cartoons, that humans have 5 senses: sight, hearing, taste, touch, and smell, as if these 5 tidy categories were nature's complete toolkit for experiencing reality, as if evolution had drawn a firm line at 5 and said, "That's enough," as if all the nuanced ways you navigate the world could be sorted neatly into those boxes and nothing more. But what if I told you that this model is not only outdated, it's wildly incomplete? That your body is not a machine with 5 switches, but a vast network of specialized detectors constantly working behind the scenes, gathering data you're not even consciously aware of. You don't just see and hear and smell. You sense balance, temperature, pain, hunger, time, direction, tension in your muscles, fullness in your bladder, and even the subtle shifts of your own heartbeat. The real number of human senses is not 5. It's closer to 15, maybe 20. Some scientists argue even more. The only reason we stick to 5 is because Aristotle said so 2,000 years ago. And since then, we've been squeezing complex biological phenomena into philosophical boxes. They simply don't fit. Let's begin by redefining what a sense actually is. Biologically speaking, a sense is any system that detects a specific kind of physical input and turns it into a signal your brain can process. If that's our definition, and it is, then balance is a sense. The vestibular system in your inner ear contains semicircular canals filled with fluid and tiny hair cells that detect rotation, movement, and gravity. You don't see when you're upside down or when you accelerate in a car. You feel it. That's not touch. That's not sight. That's equilibrium. And without it, walking would be impossible. Closing your eyes wouldn't just make you blind. It would make you dizzy because your sense of balance would lose its visual anchoring. Now consider proprioception, your body's sense of position. You can close your eyes and still touch your finger to your nose or scratch an itch on your back because your muscles and joints are constantly feeding your brain a silent map of where everything is. That's not touch either. It's position awareness. It's how you know where your limbs are without looking. Without it, your movements would be blind guesses. In fact, patients who lose proprioception due to rare neurological conditions must relearn basic movements using vision alone, like marionettes watching their own bodies from the outside. And then there's nociception, your sense of pain. Pain is not simply touch gone wrong. It's a specialized, distinct sense, governed by nociceptors that detect tissue damage or dangerous stimuli, even in the absence of actual contact. You can feel a burning sensation without touching anything, from nerve damage or inflammation or phantom limb syndrome. You can feel stabbing pain in a missing arm. You can feel agony from cold, from heat, from pressure, all processed through a system evolved specifically to detect threat, not pressure or texture. Hunger is another sense technically called interoception, the sense of your internal physiological state. You feel hunger, thirst, shortness of breath, fullness, heart rate changes, all through a subtle web of internal sensors monitoring organs you can't see but constantly react to. That churning in your stomach before a speech, that tightness in your chest during stress. Those aren't just emotions, they're sensory experiences, data from your gut, your lungs, your heart, flooding upward and informing how you feel. It's why emotions and bodily states are so entangled. And temperature, that's thermoreception. You don't feel hot and cold the way you feel rough or smooth. You have specific sensors for heat and cold that operate separately from touch. And they can be triggered by things like menthol or capsaicin, chemicals that create the illusion of temperature. Some senses even operate entirely without conscious awareness. Chronoception is your perception of time, not from clocks or calendars, but from your brain's ability to track duration, sequence, and tempo. It's what lets you tap your foot to a beat, or know how long you've been sitting in silence. It's why time feels slower when you are bored, and faster when you're in flow. Your internal clock isn't perfect. It's plastic, influenced by emotion, attention, and even body temperature. But it's real, and it is a sense. Magnetoreception, the ability to detect Earth's magnetic field, is well documented in birds, fish, and even bacteria. But recent research suggests that humans might have a vestigial form of it too. In a 2019 study, scientists placed people in a Faraday cage, shielding them from external electromagnetic fields, and then rotated a magnetic field around them. Their brains responded, not dramatically, not in a way we consciously perceive, but subtly, measurably. Our ancestors may have used this to navigate. Maybe we still do, unconsciously, like ancient birds with forgotten instincts buried deep in the cortex. Even thirst is its own sense, not just a psychological want, but a precise signal from osmoreceptors, sensors that detect the concentration of solutes in your blood. When your body needs water, those sensors scream for it, and you feel it as craving, dryness, distraction. The same goes for the sense of carbon dioxide, the buildup of carbon dioxide in your blood, which is what actually triggers the need to breathe, more than oxygen loss. If you've ever held your breath and felt the desperate urge to inhale, you were sensing carbon dioxide rise. That's chemoreception. You were sensing your own blood chemistry. And that's not touch. That's not smell. That's a hidden sense designed to keep you alive. And the more we dig, the more we find. There's baroreception, your sense of blood pressure. There's stretch receptors in your lungs that sense when to stop inhaling. There's acceleration sensors in your neck and spine. Your skin alone has pressure sensors, vibration detectors, stretch gauges, and temperature monitors, all sending different types of data through different neural pathways to different brain regions. Each one qualifies as a separate sense. Your body isn't running on 5 input channels. It's running on a symphony. But why does this matter? Isn't it just semantics? 5, 15, 20. The answer is no, because how you define your senses shapes how you understand yourself. If you believe you only have 5 senses, you might dismiss subtle bodily signals as irrational. You might ignore the gut feeling that warns you of danger, or the unexplained discomfort that signals illness before symptoms arrive. You might pathologize sensations that are actually information. You might think you're imagining things when your body is trying to tell you something real. By expanding your model of sensing, you expand your model of self. You begin to see that awareness isn't just in your mind. It's in your body, in your bones, in your blood. It's distributed, and it's constant. You are a sensing organism, always gathering, interpreting, adjusting. Consciousness is not just a theater in your head. It's a sensorium, a living interface between the world and your internal state. And the implications go beyond biology. They stretch into psychology, education, even technology. Think about artificial intelligence. Most current systems are limited to a handful of sensors, cameras for sight, microphones for hearing. But human intelligence arises from multisensory integration, from how all our senses blend, conflict, and resolve. We feel ideas, embody thoughts, smell memories. Your sense of balance affects how you think. Your gut microbiome affects your mood. Your interoception affects your empathy. Understanding the full range of senses isn't just about adding items to a list. It's about realizing that perception is the foundation of thought. If you misrepresent how you perceive, you misrepresent how you know. And in a world flooded with external stimuli, it becomes vital to listen to the internal ones, the quiet data that doesn't shout, but hums. And maybe this reawakens something ancient, a sense of wonder, because once you realize that your body is capable of sensing gravity, space, time, chemistry, rotation, hunger, memory, balance, and more, not as abstractions, but as lived inputs, you begin to see yourself not as a thinker, occasionally having feelings, but as a full-body perceiver. A being whose thoughts are shaped not just by language, but by muscle tension, temperature, and breath. And this invites a kind of humility, because no matter how much you think you know, Your body has been knowing things longer. It's been sensing since before you formed your first word. It's been steering, correcting, balancing, and interpreting a reality you've barely begun to understand. You don't just live in the world, you feel it, in ways science is only beginning to name. So the next time you close your eyes, don't imagine the world goes dark. Notice what remains. The feeling of weight pulling you downward, the tension in your calves holding you upright, the heartbeat whispering behind your ears, the faint sense of temperature on your skin, the position of your arms without needing to see them, the awareness of time passing, the space you occupy, the blood you carry, the breath you contain. That's not five senses. That's you, in full resolution, the living sum of a dozen kinds of knowing. And when you open your eyes again, you'll see the world not as something outside you, but as something you are constantly building from the inside, sense by sense, signal by signal, until the whole thing feels like reality. Your tongue can taste electricity. You've probably never questioned what flavor electricity might have. Because why would you? Wires aren't part of any cuisine, and sockets don't exactly tempt the appetite. But the next time you feel the sharp metallic zing of a 9-volt battery on your tongue, you should pause. Not because of danger, but because that tingle is proof of something wild and overlooked. Your tongue doesn't just taste sweetness, or bitterness, or salt. It can detect electricity, not metaphorically, not poetically, but literally, biologically, and instantly. It is a live wire of sensation designed to read not just molecules, but electrons themselves. And this capacity, once thought to be a weird side effect, is now being recognized as a unique sensory ability hidden in plain sight. Most people assume that taste is chemical. You eat something, and specific molecules bind to specific receptors on your tongue, which then trigger nerves to say, this is sweet, or this is sour. That's true, partly. But recent research has revealed a more electrifying truth. Some of the flavors you experience are not just chemical in origin, but electrical in nature, meaning the taste you perceive depends on tiny shifts in voltage across your tongue's surface, modulated by ions, currents, and even engineered fields. This isn't science fiction, it's neurogustation, the electric frontier of taste science. Let's start with the basics. Your tongue is covered in taste buds, which are not taste receptors themselves, but clusters of receptor cells, each with microscopic channels that detect specific types of molecules. Sugars for sweet, acids for sour, sodium for salty, glutamates for umami, and so on. When these molecules bind to their respective receptors, they cause a cascade of ion exchange that creates a small electrical signal. That signal is transmitted via cranial nerves to the brain, where it's interpreted as flavor. But here's the twist. You don't actually taste the molecule. You taste the electrical event it triggers. The taste is not the sugar. It's the voltage spike that the sugar produces in your cells. This is why certain artificial sweeteners can taste sweet, even though they're chemically different from sugar, because they trigger the same electrical response. Your taste system is not a chemical lab. It's an electrical network now. Here's where it gets stranger. Scientists have discovered that even in the absence of taste molecules, you can stimulate specific taste sensations. Using nothing but electricity, apply a mild electrical current to certain areas of the tongue, and subjects report tasting sourness, saltiness, or even metallic bitterness. This effect is direction dependent. When the current flows from the tip of the tongue to the back, it might produce a sour taste. When it flows the other way, the sensation can flip to metallic or bitter. No molecules, no food, just electrons. This means your tongue isn't passively waiting for chemicals. It's actively responsive to the movement of charge, which suggests that taste is not just a sense of substance, but a sense of energy flow. That's revolutionary. It implies that your taste system is electrically excitable in the same way your muscles and neurons are, not just chemically sensitive, but voltage sensitive. Why does this matter? Because the implications touch not only taste science, but neurology, nutrition, and even future food technology. If your tongue can taste electricity, then it can, in theory, be stimulated without calories. And indeed, researchers are developing electrogustatory devices, tiny electrodes that rest on the tongue and deliver carefully controlled pulses to simulate flavors. In one experiment, scientists at the National University of Singapore created a digital lollipop that could simulate sweet, salty, sour, and bitter sensations through electrical stimulation alone. No actual food, no chemical input, just programmed currents. In another study, Japanese researchers developed chopsticks that use mild electrical stimulation to make food taste saltier, without adding any sodium, a breakthrough for patients with hypertension or sodium restrictions. This isn't futuristic nonsense. These devices exist now. They're being tested, refined, and gradually introduced into assistive technologies for people with impaired taste or restricted diets. And yet, all this points to a deeper realization that taste is not purely about the tongue. It's about the brain's interpretation of patterns. When a current stimulates your taste buds, the brain doesn't say, "This is electricity." It says, "This is salt," or "This is sour." Why? Because it's been trained to recognize certain patterns of stimulation as certain flavors, and it doesn't care whether the stimulation comes from molecules or microcurrents. This means your flavor experience is not hard-coded. It's learned, flexible, hackable. It also explains some strange taste experiences, why you might taste metal during anxiety or illness, electrical imbalances, or why certain foods taste different during migraines or seizures, altered neural signaling, or why licking a battery creates a metallic shock, because your tongue is literally responding to the electrical field, as if it were a flavor. It's sensing charge, not just chemistry. But there's another layer to this story, one that involves evolution and survival. Why would a sense of taste evolve to detect electricity? The answer may lie in food safety. Some toxic compounds, especially in spoiled or decaying foods, release ion byproducts that alter electrical gradients. Being able to detect these changes could have helped early humans avoid danger. It also explains the metallic taste associated with certain poisons or medical treatments. You're not tasting a substance. You're tasting your own body's electrical disruption. It's a kind of sensory warning system, and it's not unique to humans. Many animals have tongues that respond to electrical fields. Some fish can even taste subtle voltage shifts in water to locate prey. In humans, this system is weaker, but still functional, an ancient survival sense repurposed for modern flavor. And if all this sounds abstract, remember this. You've likely already tasted electricity many times. That weird metallic zing from aluminum foil on dental fillings. That's a galvanic reaction, a tiny battery circuit formed in your mouth, generating current that your tongue feels as taste. That tingling from licking a 9-volt battery, that's not just discomfort, it's your taste system activating in response to electrons. And it doesn't stop there. Some food pairings enhance taste not because of their chemistry, but because of the way they alter the electrical conductivity of your saliva, changing how taste buds respond. Even the temperature of food can change the rate of ion flow, altering perceived flavor. Cold can dull sweet, warmth can amplify bitterness. The whole sensory experience of eating is an intricate electrochemical performance, and your tongue is both the stage and the conductor. So what does this mean for the future? It means that taste might soon be programmable. Imagine VR experiences where digital flavor is delivered via electrodes. Imagine culinary art that uses electrical pulses instead of ingredients. Imagine medical therapies that restore lost taste using neural implants or electro-tongue patches. These things aren't fantasy. They're in development now, but more than that, it means we have to rethink what we mean when we say taste. It's not a passive sense. It's not just buds and flavors. It's an interactive dialogue between energy, matter, and perception. Your brain is not recording reality. It's constructing flavor from electrical hints. And your tongue is not just a surface for sweetness. It's an active interface with the physics of the world. And perhaps that's the most surprising takeaway. that even in something as mundane as taste, electricity plays a starring role, that the boundary between what we think of as biological and electrical is far thinner than we ever imagined. You are an electric creature. Your neurons fire with voltage, your muscles contract with currents, your thoughts spark across synapses, and your tongue, that humble, wet, pink organ, is no exception. It too speaks in electricity, and the flavors you love, the meals you remember, the cravings that define your desires, they all begin as flickers of current, dancing across receptors, interpreted by a brain that doesn't care whether the input came from food or field, as long as it tasted like something worth remembering. So the next time you eat, pause. Consider what's actually happening. Not just molecules bonding with receptors, but electrons shifting across membranes. Voltage triggering perception, electricity becoming flavor, and you, the eater, the experiencer, not just enjoying a meal, but decoding a signal. The taste of electricity isn't fiction. It's been on your tongue all along. Your skin sees light. You might believe that only your eyes can perceive light. That vision is limited to the retina, to the rods and cones nestled in the back of your eyeballs. But what if I told you your skin, the very surface of your body, can detect light too, quietly, subtly, without any help from your eyes at all? It sounds impossible at first, like poetic exaggeration or fringe science. But this phenomenon is not speculation. It is measurable, observable, and increasingly supported by biology. Your skin, in ways that often bypass your conscious mind, is sensitive to changes in illumination, not just in the form of heat, but in light itself, including its intensity, color, and rhythm. We have long treated skin as a barrier, as something we use to feel texture or regulate temperature. It is a vast sensory organ, laced with receptors that not only interpret pressure or pain, but respond directly to light, including wavelengths that your eyes may not even notice. Some of these responses are ancient, inherited from creatures that lived before eyes ever evolved, and in your body they persist, like whispers from an evolutionary past where the skin was the first interface with the world. To understand this is to rethink what it means to see. Let's begin with what scientists call non-visual photoreception, the detection of light without the involvement of the visual system. For decades, researchers believed that only the eyes could perceive light, but studies in blind animals and humans began to uncover something strange. Even without functional eyes or visual cortices, their bodies still responded to light. Their sleep cycles shifted, their hormones fluctuated, their alertness changed depending on the time of day. This was especially baffling in individuals whose eyes had been surgically removed, people with no ocular tissue remaining. Yet their circadian rhythms still synchronized with light and dark. How was this possible? The answer came in layers. First, researchers discovered that certain cells deep within the retina, called intrinsically photosensitive retinal ganglion cells, could detect blue light independently of rods and cones. And these cells linked directly to the brain's master clock, the suprachiasmatic nucleus. But that wasn't enough to explain non-ocular light sensitivity. So they looked beyond the eyes, to the skin. In a series of groundbreaking experiments, scientists found that exposing patches of skin to light could alter biological rhythms, gene expression, and hormonal cascades, even when the eyes were covered. One 2005 study by researchers at Harvard exposed the backs of participants' knees to light while they slept and found that their melatonin production and core body temperature rhythms were altered, as though the brain had received a signal that the sun had risen. In other studies, light exposure to the skin of the chest or limbs resulted in changes in sleepiness, blood pressure, and alertness. The participants weren't aware of the light. They were in dark rooms, with no light reaching their faces, and yet their bodies behaved as if dawn had arrived. It wasn't heat. It wasn't psychological. It was photoreception, not by eyes, but by cells in the skin responding to photons. How is this possible? The answer lies in molecules called opsins, light-sensitive proteins that are found not just in the eyes, but throughout the body. Different types of opsins respond to different wavelengths of light, and many are present in skin cells, hair follicles, blood vessels, and even fat tissue. These opsins act like primitive photoreceptors. When light hits them, they trigger signaling cascades that affect nearby cells, including immune cells, pigment cells, and even neurons. For example, melanopsin, a light-sensitive protein originally identified in the retina, has also been found in human skin. Other opsins like neuropsin and encephalopsin appear in tissues far from the visual system, their function still being uncovered. But what's clear is that they are active. They respond to light, alter genetic expression, and influence biological rhythms. Your skin, in other words, may contain a distributed network of light sensors, capable of adjusting your physiology in response to your lighting environment. Whether your eyes are open or not, and the implications go far beyond academic curiosity. For instance, your circadian rhythm, your internal clock, is regulated not only by the light your eyes see, but by the light your skin absorbs. This means that artificial lighting in bedrooms or night shifts in hospitals may be affecting biological processes even in people wearing eye masks. Blue light from screens or overhead LEDs doesn't just disrupt sleep through visual pathways. It can also penetrate clothing and activate skin opsins, subtly suppressing melatonin and throwing off hormonal cycles. This could explain why even in dark rooms, people sometimes struggle to sleep if exposed to low-level ambient light their skin is still seeing. It also raises questions about light pollution, which we typically think of as a visual nuisance. In reality, it may be a physiological pollutant, affecting skin-based light sensing and throwing off our body's delicate balance between light and dark. There are other functions too. Your skin's response to light helps regulate vitamin D synthesis, but that's only the beginning. New research shows that exposure to certain wavelengths of light can improve wound healing, reduce inflammation, and even enhance mood, all through skin-based photoreceptors. Red light therapy, now used in dermatology and sports medicine, appears to stimulate mitochondrial activity in skin cells, increasing energy production and tissue repair. Some opsins in the skin may act as switches for genes involved in cell growth, apoptosis, and immune response. This means that the color of light you're exposed to may influence the rate at which your skin heals or ages, how your body manages inflammation, or how your immune system reacts to threats. It's not just cosmetic, it's biological. But the most haunting layer of this topic is psychological, because it means your mood, cognition, and sense of time may be shaped by the light your skin absorbs, not just the light you consciously see. In one study, patients with seasonal affective disorder showed improvement when infrared light was applied to their skin, even without conscious perception. In another, exposure to blue light on the skin increased alertness and working memory performance in sleep-deprived participants. Your skin may be informing your brain about the passage of time, even when your eyes are closed. It may be contributing to your internal sense of morning versus evening, readiness versus fatigue, calm versus anxiety. This turns the skin into more than a surface. It becomes a timekeeper, a mood regulator, a silent informant whispering updates to the brain about the outside world. And if that's true, then what does it mean for architecture, for education, for mental health? Should classrooms and workplaces consider the spectral qualities of their lighting, not just for visual clarity, but for skin-based signaling? Should hospital gowns be designed to permit light to the chest or back during early hours to support patient circadian alignment? Should we rethink sleep hygiene as something that involves not just darkness for the eyes, but darkness for the skin? These are not hypothetical questions. They are emerging fields of study. The skin is no longer just a tactile map of sensation. It is a perceptual gateway to time, energy, rhythm, and regulation. And perhaps this makes intuitive sense. After all, we've always associated light with life, with wakefulness, with presence. We turn our faces to the sun not just for warmth, but for orientation. Maybe deep down, part of us always knew that we don't just see the sun with our eyes. We feel it with our skin, not as heat, but as signal, not as warmth, but as awareness. Your body is not blind when your eyes are closed. It is sensing silently, precisely, the shifting story of the sky. So the next time you're standing by a window, eyes closed, feeling a subtle shift in the air, pay attention. The sunlight brushing your arms might be doing more than warming you. It might be telling your cells what time it is, guiding your hormones, preparing your sleep, or adjusting your mind's alignment with the world. You may not see it in the way you expect, but your skin does. And that quiet awareness, humming beneath the surface, is one more reminder that perception isn't limited to the senses we were taught. Sometimes you see without sight, sometimes you listen without ears, and sometimes your skin reads the light, not as brightness, but as truth. Touch can trigger emotional memory. You probably think of memory as something stored in the brain, a network of neurons that records images, smells, facts, feelings. But what if I told you that a single touch, even a light brush of skin, could unlock not just a memory, but the entire emotional experience attached to it, complete with the mood, the body sensations, even the breath pattern you had when it happened, and that your skin, your nerves, and your sensory receptors are not just receivers of the present, but keepers of the past. This isn't science fiction, it's a neurobiological truth that's both strange and intimate. Touch doesn't just connect people in space, it connects people and events across time. A sweater that feels like the one your grandmother wore. A squeeze on your shoulder that mimics how someone once comforted you. The warmth of a hand that feels just like the one that once let go. These aren't random associations. They're embodied triggers, physical sensations that reawaken stored emotional states, sometimes so precisely that you feel as if you've traveled backward into the original moment. This phenomenon is part of a field called somatic memory, the understanding that your body, not just your mind, carries traces of lived emotional experience, and that touch, more than almost any other sense, has the power to summon them without warning, without narrative, and without logic. To understand how this works, we have to look at how the nervous system processes touch. Unlike vision or hearing, which are channeled through highly centralized brain regions, like the visual cortex and auditory cortex, the sense of touch is distributed throughout the body, mapped somatotopically in the brain, in a region called the somatosensory cortex. Each patch of skin, your fingertips, your lips, your back, has a corresponding area in the brain dedicated to processing input from that region. But what's lesser known is that touch also interfaces directly with regions responsible for emotion and memory, including the amygdala, which processes fear and emotional salience, and the hippocampus, which is critical for forming and retrieving memories. When you experience something tactile during an emotional event, like being held, hurt, comforted, or injured, that sensation becomes tightly encoded with the emotional charge of the moment. It's not just you remember being hugged. Your body remembers what the hug felt like, and under the right conditions, it can bring that memory back in full emotional resolution. Studies on trauma survivors provide some of the clearest evidence of this connection. For individuals with post-traumatic stress disorder, certain touches, even benign ones, can provoke intense emotional reactions. A brush on the wrist, a hand on the shoulder, a particular texture. These can act as cues that unlock entire traumatic memories, often without any visual or verbal content. The body jumps before the mind understands. This is because traumatic memories are often non-verbal, encoded as sensory and emotional imprints rather than stories. The brain doesn't always record trauma as a linear narrative. Instead, it encodes fragments. The way the floor felt, the tone of a voice, the coldness of a hand. These fragments live in the body, waiting for a match to re-emerge. And it's not limited to trauma. Touch can also retrieve positive emotional memory. A hand clasp that reminds you of safety, a texture that evokes childhood joy, a gentle pressure that floods you with connection. These sensations are not generic, they are specific. Your nervous system knows the difference between a clinical pat and a genuine embrace, and it catalogues them with a level of detail most of us never notice. What's even more fascinating is that the timing of touch matters. During critical periods of development, especially in infancy, touch shapes not only physical growth but emotional regulation. Babies who receive consistent, affectionate touch develop stronger emotional bonds, better stress responses, and more resilient nervous systems. The sensation of being held by a parent in early life is recorded not just as comfort, but as a template for future relationships. When we're older and someone touches us in a similar way, especially in vulnerable moments, that old neural pattern lights up. The memory may not even be conscious, but the body recognizes the emotional blueprint. This is why a particular embrace can make you feel safe, for reasons you can't explain. It's why certain people's touch makes you trust them instantly, while others cause discomfort. Even without any words exchanged, your body is matching current input to old emotional codes, most of which were written long before you could speak. This has enormous implications for everything from therapy to everyday relationships. In trauma-informed care, therapists sometimes use somatic techniques, safe, consensual touch or body-based awareness, to help clients process emotional experiences that are not accessible through talk alone. In palliative care, gentle touch has been shown to reduce anxiety and increase peace, even in patients with advanced dementia. In long-term couples, even brief affectionate contact, holding hands, a hand on the knee, is associated with reduced stress hormones and increased emotional attunement. These aren't gestures, they're neurological interventions. Touch is a bridge, not just between people, but between past and present, between memory and moment. And your skin, your muscles, your fascia, all of them hold keys to experiences your conscious mind may have forgotten, but your body remembers with eerie clarity. But the reverse is also true. Lack of touch in formative moments, or in adulthood, can lead to emotional disturbances, including anxiety, depression, and impaired social bonding. This is called touch deprivation, and it highlights just how essential tactile input is to human emotional well-being. We often think of touch as optional, nice, but not necessary. Yet your nervous system disagrees. From the moment you're born, it relies on physical contact to organize itself. When that input is missing or interrupted, the emotional consequences can be profound. Even in adulthood, people who receive regular affectionate touch report higher levels of oxytocin, the bonding hormone, lower levels of cortisol, the stress hormone, and increased sense of safety and connection. Your brain expects touch, not just as stimulation, but as emotional feedback. And when it doesn't get it, it listens more closely for echoes from the past. That's why certain textures, temperatures, or pressures can awaken buried emotional experiences. The nervous system is searching its memory for comfort. All of this paints a picture of memory that is not stored like a library of facts, but scattered throughout your body like emotional fingerprints, each one waiting for the right sensory key to unlock it. And that key is often touch. Not dramatic or invasive, just precise. A certain pressure, a certain motion, a certain rhythm. Even the texture of clothing, the sensation of sheets, or the feel of rain can summon emotional scenes with startling immediacy. And because the body is faster than thought, you may feel something long before you understand why. That surge of joy or sadness or safety, that's your nervous system recalling something your brain hasn't yet caught up to. And this isn't mystical, it's measurable. It's rooted in somatosensory integration, neuroplasticity, and effective neuroscience. Your body is not just reactive, it's reflective. It remembers through sensation, and touch is its preferred language. So what does this mean for how we live? It means we should pay more attention to the emotional power of everyday contact. The hug you offer, the hand you hold, the way you sit next to someone in silence. It means recognizing that physical closeness is not just physical. It is psychological. It is historical. It is a living archive of connection. It also means that when we feel sudden, unexpected emotions for no clear reason, especially in response to being touched, we should not dismiss them. The body may be remembering something it hasn't been able to say. And by listening to that response, we give memory a voice beyond language. Because in the end, touch is more than sensation. It is memory. It is emotion. It is identity etched into flesh. When someone touches you with kindness, with familiarity, with care, your body listens. And sometimes it answers back with echoes from long ago. You hear before you were born. Before you opened your eyes to light. Before your skin felt the cold air of a delivery room. Before your lungs knew breath. You were already listening. Not with perfect clarity, but with presence, with responsiveness, with the kind of primitive awareness that predates language and lingers long after it. Inside the womb, surrounded by fluid and muffled darkness, your ears began functioning around the 25th week of gestation. And from that point on, sound was your first window into the outside world. Not light, not sight, not even touch in the way we know it, but sound. And not just passive vibration, real auditory perception. You didn't understand the meaning of words, of course, but you absorbed their rhythm, tone, and cadence. You registered your mother's voice, not as language, but as melody, her laughter, the tempo of her breathing, the tempo of her stress. Her body became your soundtrack, and your earliest experiences of comfort, safety, or anxiety were wired through the echoes of her world. This fact alone should stop you, because it means that your first sensory experiences weren't your own. They were borrowed from someone else's heartbeat, someone else's voice, someone else's environment, and that's not a poetic idea. That's fetal neurobiology. Studies in prenatal auditory development have confirmed that fetuses respond to external sounds in the third trimester, including music, voices, and environmental noise. Using ultrasound imaging and heart rate monitoring, researchers have found that fetuses react to sound stimuli with movements, changes in heartbeat, and even rudimentary forms of habituation. They become less responsive to repeated sounds and more responsive to new ones. A basic sign of learning. This means that memory formation begins before birth, and the content of that memory is rooted in sound. When mothers read a story repeatedly in the final weeks of pregnancy, newborns show a clear preference for that story when played after birth, even if it's read by someone else. The melody of the voice, the rhythm of the syllables, these become familiar and calming, and that's not limited to literature. Infants also show recognition of music they heard in the womb. Songs played during pregnancy can soothe newborns days or even weeks after birth. And the effect is stronger when the sound is associated with emotional calm in the mother. This is more than cute anecdote. It's the earliest evidence of effective auditory imprinting, where emotional states are encoded alongside sensory input, a foundational layer of memory formation, and a clue that our earliest learning is not visual or logical, but auditory and emotional. And the sounds aren't all external. Inside the womb, you heard the constant internal orchestra of the maternal body, her blood rushing, her digestive gurgles, her breath cycling in and out, and most importantly, her heartbeat, which was not only a physical vibration, but a regulator of your own rhythm. The maternal heartbeat serves as an internal metronome for fetal development. And its consistency is so fundamental that deviations in this exposure have been linked to developmental differences. That's why newborn incubators often include heartbeat simulators, because the absence of that steady pulse can leave premature infants disoriented and dysregulated. But the real magic is that your auditory system learned how to respond to the world from inside another person. You learned what calm and chaos sounded like, long before you knew what they meant. And this foundational mapping influences how you relate to voices, music, and tone for the rest of your life. The reason some voices feel safe and others feel threatening might not just be cultural or social. It might be proverbial. Now consider this. The fetal ear isn't just a passive structure, it's actively sculpted by experience. Auditory neurons strengthen or weaken based on the variety and frequency of sound exposure in noisy environments, urban settings. For example, fetuses can become desensitized to certain frequencies. In contrast, babies raised in quiet environments may have increased sensitivity to subtle auditory changes. This shapes not only the child's later auditory preferences, but potentially their language development, emotional processing, and even musical inclination. Some studies suggest that exposure to tonal languages like Mandarin in the womb can prime the brain to process pitch-based language more efficiently later in life. Likewise, infants exposed to multiple languages before birth show increased neural flexibility in language regions. These aren't deterministic outcomes, but they are compelling indicators that your auditory world doesn't begin at birth. It begins in utero, and it matters more than we once believed. But perhaps the most mind-bending realization comes when we consider that fetal hearing operates in a very different acoustic environment from ours. The womb is filled with amniotic fluid, which changes how sound travels. High frequencies are dampened, low frequencies carry more effectively, so your first auditory experiences were low, pitched, muffled, and rhythmic, almost like underwater music. This might explain why white noise, heartbeat rhythms, and low humming sounds are so calming to infants. They resemble the sonic landscape of the womb. Even adults often find deep comfort in similar sounds: ocean waves, gentle fans, or heartbeat. Like drums, it's possible that our preference for these sounds isn't just aesthetic, it's neurological nostalgia, a return to our first known environment. The sounds we heard before we were born might be the ones we carry for life, etched into the deepest layers of the auditory cortex, forever linked to our first sense of safety. And this idea that you began forming emotional and sensory memories before birth challenges much of what we believe about where consciousness begins. If the brain is already processing input, forming preferences, and linking emotion to experience in the womb, then the border between pre-life and life becomes fuzzier than we thought. It also gives new weight to maternal well-being. A stressed or soothed mother doesn't just affect her own body, she transmits emotional tone through her voice, her breathing, and her physiology, all of which become part of the unborn child's first sensory education. In this way, auditory development is also emotional development, and it continues long after birth, shaped by every lullaby, every whispered word, every rising argument. So next time you hear a sound that stirs something inexplicable in you, a voice, a melody, a rhythm, consider that it might not just be from your childhood or your culture. It might be older. It might be the first thing you ever knew, the first pattern your brain ever trusted before light, before faces, before even your own breath. There was sound, and that sound is still inside you, echoing in the most ancient corners of your nervous system, reminding you that you didn't just come into the world ready to learn. You were already listening. Smell is tied strongest to memory. It's strange how a scent can catch you off guard, how something as invisible and fleeting as a wisp of perfume, the dampness of old wood, or the faint trace of rain on asphalt can crack open the past more powerfully than a photograph ever could, pulling you into vivid emotional landscapes you didn't even know you still carried. It doesn't knock on the front door of your mind like logic does. It slips in sideways, bypassing words entirely. And that's because smell, unlike any other sense, travels a shortcut to memory. Not through explanation, but through emotion. Not through the thinking brain, but through the feeling one. While sight and sound take the long route through the thalamus, the brain's relay station, smell skips that detour and goes straight to the amygdala and hippocampus, regions responsible for processing emotion and encoding memory. Which is why you don't just remember your grandmother's kitchen when you smell cinnamon. You feel it, the warmth, the safety, the sunlight bouncing off linoleum, the way her voice softened when she spoke your name. It's not just a recollection, it's a reenactment. And this isn't just poetic phrasing. It's supported by olfactory neuroscience, which has revealed that smells are processed in the olfactory bulb, located at the bottom of the brain just behind the nose, which is tightly wired to the limbic system, the emotional core of who you are. That's why smell-based memories often feel more emotional, more visceral, and more whole than those triggered by other senses. They don't require narrative. They just arrive, complete, haunting, immediate. What makes this connection even more fascinating is how specific and persistent olfactory memories are. Unlike visual or auditory impressions, which fade or get overwritten with time, scent memories can remain dormant for decades and still return with full emotional potency. A 40-year-old can smell a certain type of laundry detergent and feel like they're 6 years old again, not because they remembered, but because their brain never forgot. And it's not just humans. In animal studies, rats conditioned to associate certain smells with safety or fear exhibit lasting behavioral changes, even when the scent is reintroduced long after the initial exposure. But in humans, what's especially striking is that these memories are often unconscious. You may not even know why a certain scent makes you anxious or nostalgic. The conscious mind may have lost the story, but the body, and especially the limbic system, kept the score. That scent-based emotional tagging is called associative encoding, and it's one reason marketers use scent in branding, like the smell of popcorn in cinemas or leather in luxury stores. And why hospitals sometimes use essential oils to reduce patient anxiety. Your olfactory system is not just smelling the air, it's mapping emotion onto it. Now, here's where things get even more profound. Your sense of smell is older than your conscious mind. Evolutionarily, the olfactory system predates the neocortex. It's one of the most ancient sensory systems, even found in primitive animals without complex brains. For our ancestors, smell was survival. It helped detect predators, spoiled food, or mates, long before words or reasoning existed. That ancient wiring remains. You don't need to think about a smell to react to it. Your body already knows. And that knowledge often carries with it the emotional residue of previous experiences, especially those from early childhood, when the brain is forming its foundational emotional patterns. In fact, research suggests that the first years of life are when olfactory, emotional links are most powerfully forged, which is why smells from childhood have such enduring impact. These scents become part of your emotional identity, shaping not just what you remember, but how you feel in the present. Smell also has a curious relationship with grief and loss. Many people who've lost loved ones report sudden waves of emotion when they catch a familiar scent: cologne, a favorite dish, the way a coat smells after hanging in the same closet for years. These aren't hallucinations. They're sensory echoes, fragments of presence encoded into molecules, released into the air, and decoded by a nervous system that still wants to hold on. Smell becomes a bridge to the past, not just to memory, but to connection. In this way, the olfactory system plays a quiet but sacred role in mourning, memory, and the maintenance of emotional bonds. Some researchers even propose that scent could be used therapeutically to help re-access positive emotional states in patients with depression or PTSD by identifying and reintroducing specific smells that are emotionally grounding. Smell, in this sense, becomes not just a trigger, but a tool for healing, for remembering, for anchoring identity. But perhaps most humbling of all is how little attention we give it. In the hierarchy of senses, smell is often dismissed as primitive, unimportant, or secondary. We say seeing is believing, not smelling. We trust sight and sound but treat scent as background noise. And yet, when we lose it, as many did during recent global illnesses, the psychological effects are severe. loss of smell isn't just inconvenient. It can be disorienting, depressing, even identity erasing. Because without smell, food becomes bland, places lose their personality, and memories become harder to access. Smell gives texture to life, and when it's gone, the world flattens. So the next time a familiar scent makes you stop in your tracks, when it causes your heart to ache or your lips to smile without warning, pause before brushing it off. What you're experiencing isn't just a smell, it's a living archive of who you've been, of the places that shaped you and the people who once meant the world. Smell is memory, not in words, but in emotion, in silence, in breath. And when it rises, uninvited and unmistakable, it's your brain reminding you that the past is never really past. It's just waiting in the air. Eyes can detect polarized light. There's a hidden layer to the light around you, a secret structure woven into every beam that your eyes were never trained to see, but might just be whispering to you anyway, quietly influencing your perception without your awareness. It's called polarization, and although most people think the human eye is blind to it, science has discovered something far more curious. You can see it, just barely, if you know where to look and what to feel. Because your visual system, though crude compared to the eyes of bees or mantis shrimp, is not entirely indifferent to this subtle quality of light. In fact, under specific conditions, your retina responds to polarized light patterns in ways that suggest an ancient visual ability, long thought to be dormant or absent in our species, still flickering beneath the surface of consciousness. This isn't science fiction or wishful thinking. It's supported by real experiments involving what's known as Heidinger's brush, a fleeting, ghost-like visual pattern that appears when you gaze at polarized light on a blue background. You won't see it in your peripheral vision. You won't even see it clearly, but if you stare long enough at the white center of a polarized LCD screen, or the sky 90 degrees from the sun, you might notice a faint, yellowish bow tie or halo, shaped like two crossed brushes. And what you're seeing, however dimly, is your brain's interpretation of polarization, filtered through your cornea and the aligned microstructures of your macula lutea, a small region at the center of your retina that behaves like a natural polarimeter. This phenomenon is subtle, fleeting, and easy to miss, which is why most people go their entire lives without noticing it. And yet, it reveals something profound. Your eyes are capable of detecting more than you were ever told, more than textbooks list, more than the five senses model allows. To understand how this works, you need to know what polarized light actually is. Light, at its most basic, is an electromagnetic wave. It oscillates as it travels, with the electric field vibrating in different directions. Ordinary light, like sunlight, or a bulb's glow, contains waves vibrating in all directions, but polarized light is filtered. The waves vibrate in a single direction. This can happen naturally, such as when sunlight scatters in the sky or reflects off water, or artificially, using polarizing filters in photography or LCD screens. Many animals, like bees, ants, cuttlefish, and birds, use this property of light for navigation, hunting, and communication. Humans, it was long believed, couldn't detect it at all. But the discovery of Heidinger's brush in the 19th century, and its modern confirmation through neuroscience and optics, suggest that our retinas have some sensitivity to polarization, albeit minimal and subconscious. This residual capability likely stems from an evolutionary past, where such a sense may have been more useful before our species adapted to rely primarily on contrast, color, and motion in open terrestrial environments. More interestingly, the human eye isn't sensitive to polarization through rods and cones, the usual photoreceptors responsible for night vision and color, but through the macular pigment, a layer of yellowish carotenoids concentrated at the center of the retina. These pigments are organized in a radial pattern and are birefringent, meaning they interact differently with light depending on its polarization. When polarized light passes through this structure, it produces interference patterns that the visual cortex interprets as the ethereal figure of Heidinger's brush. It's not like seeing color or shape. It's more like seeing the memory of a shadow that doesn't belong to any object. And though most people need training or controlled conditions to observe it, the fact remains, our eyes can detect polarized light, even if only vaguely. This faint capacity has been harnessed in certain scientific and medical contexts. For example, polarized light testing can reveal macular degeneration and other retinal conditions because changes in macular pigment alter the visibility of Heydinger's brush. Some experimental therapies even use polarized light exposure to track visual processing in neurological research. But beyond biology, what's striking is the philosophical implication. We're surrounded by more than we see. Literally, not metaphorically. Literally, the light entering your eyes carries information you were never taught to interpret. And yet, under the right conditions, your mind does interpret it. Not with clarity, but with suggestion. This means perception is not just about what your senses are designed for, but also about what your brain chooses to notice. And that opens an even deeper question: how many other layers of reality slip past you every day simply because you were never taught to name them? The polarization of light is only one example, but it's a perfect one, because it exists everywhere, all the time, embedded in reflections, skylight, and screens. It influences how fish hide, how birds migrate, how cameras take photographs, and your eyes, imperfect, human, clumsy, are still a little bit sensitive to it. That ghost-like bow tie you might have mistaken for an afterimage or optical illusion isn't just a trick, it's a leftover sense, a window into a deeper structure of the world, a visual echo of something just outside your reach. And perhaps that's the real lesson here, that even in something as supposedly well mapped as vision, there are still mysteries, still capabilities we overlook. The eye, often reduced to its rods and cones in school diagrams, holds more nuance than most realize, not just in how it sees light, but in how it whispers to the brain about the hidden geometries within it. You might not use polarized light to navigate a forest like an ant, or see underwater like a shrimp, but your body hasn't fully forgotten that it once could detect more, and that faint residue remains. So next time you look up into a clear sky, or stare at a screen a little too long, remember that something ancient is still flickering beneath your conscious vision. Not imaginary, not magical, just quietly real, like a voice speaking in a forgotten dialect. Your eyes are still trying to tell you more than you know how to hear. Taste changes based on sound. If someone told you that the crunch of a chip, the hum of an air conditioner, or the background music in a cafe could subtly change the way your food tastes, you might instinctively reject the idea. Taste, after all, sweet, salty, sour, bitter, umami, a neat palette of flavors, locked to the receptors lining your mouth. But the deeper truth, often ignored, is that taste is not a standalone sense. It's a deeply integrated multisensory event, influenced not just by smell or texture, but by the sounds around you, and sometimes the sounds you're not even aware you're hearing. What we call flavor is not located solely in the food or the tongue. It is a creation of the brain, a synthesis of expectation, context, emotion, memory, and sensory inputs. And sound, surprisingly, is one of its strongest hidden collaborators. Scientists have been exploring this strange relationship under a fascinating field called sonic seasoning, where changing the pitch, tempo, or timbre of background sound can alter how people perceive the intensity or quality of a taste. For example, high-pitched sounds tend to enhance perceived sweetness, while low-pitched or brassy tones tend to bring out bitterness. You're not imagining things when a piece of chocolate tastes richer while listening to violins, or when your cocktail feels flatter under harsh electronic noise. You're experiencing the acoustic modulation of flavor, a real and measurable phenomenon grounded in neuroscience and psychoacoustics. To grasp how this works, we need to understand the integration hubs in your brain, like the orbitofrontal cortex, which merges information from multiple senses: smell, taste, vision, touch, and sound into a single coherent experience we interpret as flavor. This region doesn't treat inputs in isolation. Instead, it uses cross-modal correspondence, meaning it draws associations across senses to form predictions and assign meaning. So if a certain sound suggests a flavor, your brain adjusts its interpretation accordingly. A sweet dessert accompanied by bright, tinkling music may taste sweeter, not because your taste buds change, but because your brain expects sweetness, enhances those signals, and downplays conflicting ones. In one famous experiment by researcher Charles Spence, participants drank the same cocktail twice, once with high-pitched music and once with low-pitched, and reported it tasted sweeter with the high tones and more bitter with the low. Another study used crisps that had identical salt levels but were paired with either Fresh's crunchy sounds or duller ones. The louder and crispier the sound, the fresher and tastier the crisps were perceived. These aren't isolated tricks. They reveal a systemic truth. Your perception of taste is context dependent, and sound is part of that context. Even ambient noise affects your palate. Airline food is notoriously bland, and while altitude and dryness play a role, researchers discovered that constant engine noise, typically around 85 decibels, reduces the perception of sweetness and saltiness, while increasing the intensity of umami. That's why tomato juice, rich in umami, is disproportionately popular on flights. It actually tastes better in that environment. The implications extend into real life. A bustling restaurant, a quiet dinner at home, or even the background score of a food commercial can all unconsciously tweak how food feels in your mouth. Music, in particular, acts as a flavor enhancer or suppressor, guiding mood, attention, and even hormonal response, all of which feed into how we perceive taste. The effect is so reliable that companies like Oxford's Cross-Modal Research Laboratory have worked with chefs and brands to design custom soundtracks that elevate specific dishes, creating immersive culinary experiences where every bite is enhanced, not by spice, but by sound. This blending of auditory and gustatory art has birthed a new frontier of neurogastronomy, where composers and chefs collaborate, not to distract, but to direct the senses, tuning flavor through audio. From a biological standpoint, this makes evolutionary sense. Our ancestors didn't evaluate food in sterile silence. The natural world was noisy, and sounds likely signaled safety or threat. Crunching leaves while eating might indicate danger. Birdsong may imply calm and safety. Over time, we may have developed subtle associations between auditory input and food quality. But even today, your own chewing sounds, amplified through bone conduction, feed back into the perception of freshness and texture, which is why a muted crunch can make a chip seem stale, even if it's not. This feedback loop is so powerful that experimental earbuds have been created to alter the pitch of your own bite, allowing researchers to simulate freshness or softness just by adjusting sound. Your ears, it turns out, are part of your mouth's experience, even if you never realized it. There's something deeply humbling about this discovery, that something as invisible as air pressure fluctuations can shape the way sugar tastes on your tongue. It challenges the illusion that we are rational, isolated evaluators of the world. Instead, it suggests that experience is a collaboration between body and world, and that our senses, far from being separate, are in conversation with each other at all times. The meal you remember most might not just owe its magic to the food, but to the laughter at the table, the music playing softly in the background, the clinking of glasses. It's all part of the flavor, and once you understand that, you begin to see just how malleable and rich our perception of reality truly is. So next time something tastes off, ask yourself, is it the food or the soundscape? And when something tastes better than usual, notice what you are hearing. Perhaps it is not just flavor in your mouth, but harmony in your environment. The world doesn't just feed you through your tongue, it flavors your life through every sense you have, including the ones you didn't think mattered. color affects pain perception. When we speak of pain, we usually imagine something physical. A cut, a burn, an ache deep in the body. Something sharp and obvious and felt where it happens. Not something that might be quietly shaped by something as abstract and distant as color. And yet, the science is clear. What you see can deeply influence what you feel, and not metaphorically. Literally, the color of your environment, the lighting in a room, even the hue of the object delivering a painful sensation. All of it can alter your perception of pain in measurable and predictable ways. It is not that red makes things hurt more, because red means danger, or that blue soothes, just because we associate it with water and sky. It is far more intricate, a collaboration between the brain's emotional, sensory, and visual networks that rewrites how we register pain before we're even conscious of it. Your pain is not purely physical, it's filtered, shaped by expectation, association, and the visual cues that silently prime your nervous system to anticipate more or less threat. And color, it turns out, is one of the most powerful primers of all. In experimental settings, people report lower pain ratings when exposed to blue and green hues, and higher pain ratings with red, black, or dark environments, even when the stimulus is identical. One study, for instance, found that participants placed their hands in painfully cold water, while viewing red or orange lighting described the pain as more intense and intolerable than those immersed under blue or white lighting. The physical temperature was exactly the same. The only difference was what they were looking at. Another study using laser-induced heat pain revealed that pain thresholds increased, meaning people tolerated more heat when the beam appeared blue and decreased when it was red. That color alone, even when artificially attached to a heat source, was enough to convince the brain to expect and amplify discomfort. This is because color is not just a passive reflection of light. It's an evolutionarily conditioned signal, deeply tied to our survival instincts. Red, for example, is associated with injury, inflammation, blood, heat, and alarm. Blue is tied to coolness, distance, and calm. Green suggests safety, nature, rest. These associations aren't just cultural. They're deeply embodied, wired into how our autonomic nervous system responds to threat. Your pupils constrict in bright red light, your heart rate subtly shifts under different tones, and your perception of pain, it dances along with these cues. But it goes deeper than just broad color categories. Subtle shifts in saturation, brightness, and context also matter. A red scene in a hospital versus a red scene in a romantic dinner may register differently because the environment primes the emotion. This is why pain clinics and pediatric wards often use pastel blues, seafoam greens, or warm neutral colors in their design. Not just for aesthetics, but for neurological modulation. Some even go so far as to project calming visualizations, flowing water, forest leaves, sunset gradients. Because research shows these reduce the need for pain medication during recovery. Color is being harnessed clinically, not as decoration, but as non-pharmacological pain relief. And the effect isn't limited to walls or lighting. Even the color of pills affects their perceived strength. Red and orange pills are seen as more stimulating. Blue and green are perceived as more calming or sedative. This expectation, in turn, modifies the body's real response. An extension of the placebo effect, where belief guides biology. Why does this happen? Because pain is not a direct signal from body to brain. It's a complex interpretation, a story your nervous system builds based on context, memory, emotion, and yes, visual input. The visual cortex is tightly connected to the anterior cingulate cortex and the insula, regions involved in both emotion and pain regulation. This means what you see doesn't just accompany what you feel, it can modulate it. It also explains why phantom limb pain can be reduced through visual tricks like mirror therapy, and why burn victims often find relief by engaging with cool-colored virtual environments. Your brain is constantly weighing visual safety cues against sensory alarms, When the visuals say, "This is dangerous," pain increases. When they say, "This is okay," pain eases, even if the actual stimulus doesn't change. This interplay is subtle, subconscious, and yet profoundly powerful. It also makes you wonder how much of your own pain is shaped by your surroundings, without your awareness. If a red hospital room makes you flinch more, or if a soft green wall helps you breathe a little easier, what does that say about how real pain actually is? Not that pain is imagined, but that it's interpreted, colored, tuned, which opens a new kind of responsibility, not just for doctors and designers, but for all of us, to become stewards of the environments we create, because they may be hurting or healing more than we realize. Even something as seemingly small as changing the wallpaper in a waiting room or adjusting the light in your bedroom could be influencing how your body processes discomfort. Pain isn't just a matter of biology, it's a matter of perception, and perception is vulnerable to beauty suggestion and light. So the next time you feel overwhelmed by a dull ache, a tension in the back of your neck, or a lingering soreness that won't let go, take a moment to look around. What colors surround you? What tones are bathing your skin? You might be surprised to find that your nervous system is reading the room long before you consciously notice it. Pain, you see, is not just felt. It is seen, shaped, and softened, not always by medicine, but sometimes by a shift in hue. Your ears detect motion. You might think your ears are built solely for sound, to decode the vibrations of air into the melodies of music, the meaning of words, the warning of a siren, or the comfort of a whispered voice. But your ears are doing far more than you realize. They are quietly, constantly detecting motion, not just outside you, but within you, shaping your balance, posture, direction, and even your sense of reality, without ever demanding your attention. What you call hearing is only one part of what your ears are designed to do. Hidden deep inside them, beyond the eardrum, past the cochlea that translates sound waves into nerve impulses, lies the vestibular system, a delicate and ancient structure, filled with tiny canals and fluid. Filled chambers that silently track every movement of your head, every tilt, every rotation, every acceleration or stop. It's not your eyes or your skin or your muscles that tell you which way is up when you close your eyes. It's your ears. More precisely, the semicircular canals and otolith organs inside them, which sense angular and linear motion. These structures are exquisitely sensitive, capable of detecting movements as small as a degree per second, and fast enough to compensate for head turns, before your brain even finishes processing the visual scene. It's why you don't see the world blur when you shake your head. It's why you can walk in the dark without falling over. And it's why, when this system is damaged, by injury, disease, or even a fast spinning carnival ride, your world can feel like it's spinning, tilting, or collapsing into disorientation. You feel dizzy, not because your eyes are confused, but because your ears are telling your brain a story that doesn't match the one your body expects. But there's more, because the motion your ears detect isn't just about keeping you upright, it's about how you navigate the world. The vestibular system works in concert with your proprioception, your body's sense of internal position, and your visual system to form what scientists call the sensoromotor integration, the map your brain builds of your place in space and time. When you turn your head, your eyes automatically shift in the opposite direction to stabilize your gaze, thanks to the vestibulo-ocular reflex, a rapid involuntary adjustment that happens in milliseconds, faster than conscious thought. This ability is so crucial that when it malfunctions, people experience blurred vision with movement, nausea, and a loss of spatial orientation, like seasickness or vertigo. And here's the truly fascinating part. Motion itself can be heard by the auditory system in ways we rarely notice. For instance, some neurons in your auditory brainstem are specifically tuned to changes in sound location, meaning they fire more, not just when something is loud or soft, but when it moves. Your ears can detect the direction and velocity of moving sound sources, calculating differences in timing and intensity between your two ears. With such precision, that you can tell whether a mosquito is circling your left ear or approaching from behind, even with your eyes closed. And in the animal kingdom, this ability becomes even sharper. Owls can detect prey in total darkness by sound motion alone. Bats use echoes not just to locate, but to track movement in space, reconstructing a dynamic auditory map of their surroundings in real time. While we don't echolocate with that level of finesse, humans too rely on these subtle motion cues more than we think. In sports, driving, walking in crowds, or even simply listening to someone speak while they walk past us. And yet, the vestibular system's role in cognition is just beginning to be understood. Recent neuroscience shows that motion signals from the inner ear influence attention, emotion, and even memory. Patients with vestibular disorders are more likely to develop anxiety, depression, and derealization. Not just because dizziness is unpleasant, but because the brain relies on vestibular cues to feel grounded in reality. When those signals are disrupted, people often describe feeling disconnected, like the world isn't real or their body isn't theirs. In fact, some researchers believe that the vestibular system plays a hidden role in embodiment, your sense of being located in a physical body moving through space. There's evidence that vestibular stimulation, like gentle rocking or even spinning, can affect problem-solving ability, emotional regulation, and visual spatial reasoning. And think of how often we use metaphors of motion to describe thoughts. I'm feeling off balance. My head is spinning. I need to regain my footing. These aren't poetic flourishes. They reflect the deep interweaving of motion and mind, of physical equilibrium and mental clarity. Even dreams of flying or falling may stem from the vestibular system's neural echoes, traces of motion replayed by the brain during sleep. Some studies even show that electrical stimulation of the vestibular nerve can induce motion illusions, or even enhance certain types of memory and attention, suggesting that your ears are part of a far larger cognitive architecture than previously known. What makes all of this even more extraordinary is that this motion sensing system operates without sound. You don't hear it, but it hears you, the microtilts of your head, the vibration of footsteps, the turn of your body when no sound is present. In many ways, your ears are your internal gyroscope, not only orienting you to the world, but orienting the world inside your mind. Every time you move and stay upright without thinking, every time you close your eyes and still know which way is up, every time you follow a moving voice in the dark, that's your ear detecting motion, not just sound. It makes you wonder, how much of your confidence, balance, and presence depends on something you never consciously notice? What happens when we lose this inner compass, when the signals go silent or get scrambled, and the world begins to shift beneath our feet, not because it moved, but because we can no longer hear our own movement through it? So the next time you tilt your head thoughtfully, or spin to catch a voice, or steady yourself while walking a narrow path, remember that your ears are doing more than listening. They are measuring, guiding, grounding you not only in sound, but in space itself. Without them, the world doesn't just go quiet. It goes unstable, and in that silence, you might realize that hearing isn't only about sound waves. Sometimes, it's about detecting the invisible movements that keep your world upright. Cold and wet feel the same to your brain. There's a curious confusion your body quietly harbors, one that rarely reveals itself unless you stop to feel it. The strange way your brain can mistake cold for wetness and wetness for cold, as if temperature and texture were being woven together on the same invisible thread, tangled before ever reaching your conscious awareness. You've likely felt it before, stepping barefoot onto a bathroom tile in winter and recoiling certain it's wet, only to find it bone dry, or reaching for a metal railing outside and instinctively assuming it must have rained, because the chill against your skin mimics moisture so precisely. This isn't clumsiness in perception. It's a deep quirk in the architecture of your sensory system, one that reveals just how intertwined your touch, temperature, and pattern recognition truly are, and how much of what you feel is an inference, not a fact. The skin, your body's largest and most exposed organ, holds a variety of specialized receptors, some that sense pressure, others that detect vibration, some for temperature, and a few for pain. But no receptor exists solely for detecting wetness. Instead, the sensation of wetness is reconstructed by your brain using clues: a drop in temperature, increased skin conductance, subtle skin deformation, and even pattern recognition from previous experiences. Your nervous system builds the concept of wet by combining these signals in a kind of sensory hallucination, and cold, with its ability to mimic the cooling effect of evaporation and the sudden shock of moisture, plays a starring role in that illusion. This connection is so robust that in experimental settings, researchers can consistently trick participants into reporting a wet feeling simply by applying cold objects to the skin, without any moisture at all. One study used dry metal rods, cooled to different temperatures, and touched them to participants' arms and hands. At certain temperatures, particularly between 20 degrees Celsius and 25 degrees Celsius, subjects overwhelmingly reported the sensation as wet, even though their skin remained dry throughout. The colder the object, the more intense the reported wetness. And conversely, when actual moisture was applied at body temperature, participants were less likely to describe it as wet, unless the surface was also cool. What this suggests is not just that cold can simulate wetness, but that your brain relies heavily on temperature cues to make that judgment. Why? Because, biologically speaking, most things that are wet also tend to be cooler than your body: water, mud, rain, sweat. And so, over time, evolution has wired your nervous system to pair coolness with dampness. This pairing becomes so deeply rooted that the presence of cold alone is enough to trigger the assumption of wetness, regardless of whether any liquid is present. It's a shortcut, efficient, usually reliable, but not infallible. And it shows just how suggestible your senses truly are. The implications go far beyond a few misread tiles or metal poles. This blending of signals affects everything from how athletes perceive sweat, to how burn victims register skin contact, to how virtual reality developers simulate environmental realism. For example, VR engineers often use cold airflow or cooled surfaces to mimic the feeling of water or rain. Not because they're actually adding moisture, but because cold alone convinces the brain that wetness is happening. The illusion is strong enough that users reflexively react, flinching or adjusting posture, even when no fluid is present. Similarly, in medical prosthetics, artificial limbs that incorporate temperature feedback, especially subtle cooling, are reported to feel more realistic, or alive, than those relying on vibration or pressure alone. Our sensory models, it seems, are built on overlap, not isolation, and that overlap isn't limited to cold and wetness. The same neural circuits that help detect pain, for example, are also involved in sensing extreme cold, which is why touching ice for too long starts to hurt, and why frostbite can mimic the sharp burn of heat. But with cold and wet, the overlap is particularly quiet, deceptive, and tied to the perception of comfort or danger. Imagine walking outside barefoot on a summer evening after the rain, stepping on a patch of stone that feels cool and slick. Your body registers it instantly: wet, slightly cold, possibly slippery, and your mind makes decisions: tread carefully, adjust balance, anticipate the feel of moss or algae. But remove the water, keep the temperature, and the same neural response occurs. This has evolutionary advantages. Our ancestors who assumed that cool surfaces were wet may have avoided mold rot or cold water hazards. But it also has psychological effects. People rate identical surfaces as less clean or more unpleasant if they feel cool upon contact, because that coldness hints at dampness, which hints at decay, germs, or danger. This sensory triangulation is not logical. It's emotional, embodied, and historical, and it leads to profound questions. How much of what you think you feel is simply a guess, based on patterns your brain learned long ago? How often do you react not to the world as it is, but to what your skin thinks it might be. This sensory illusion also plays a subtle role in comfort design. From car seat materials, to bed linens, to baby wipes. Because the temperature of contact affects how we judge cleanliness, freshness, and safety. A wipe that feels room temperature may seem dry or ineffective. Cool it slightly, and it suddenly feels wetter, fresher, more hygienic. Similarly, certain athletic clothing uses phase change materials that cool upon sweat contact, enhancing not only thermal regulation, but the sensation of moisture removal, essentially tricking the skin into feeling drier, faster. These small design choices rest on a deep truth. The skin's perception is not objective, but inferred. It constructs wet by interpreting a constellation of signals, and among them, cold is king. So the next time you step into a chilly room and mistake the air for dampness, or touch a cold glass and flinch at the phantom slickness, remember, you are not malfunctioning. You are experiencing one of the brain's most elegant tricks, the borrowing of meaning from sensation, the silent handshake between cold and wet that evolved to keep you safe, but now lives on as a beautiful confusion, one that reminds you that your reality is never raw input, but always, wonderfully, an interpretation. Blind people can echolocate. You might assume that vision is the primary gateway to perceiving the world, that once sight is lost, the surrounding landscape fades into abstraction. But there exists a quiet and astonishing skill, developed not by technology but by the human brain itself, that allows some blind individuals to perceive space using nothing but echoes. A biological sonar known as echolocation, which transforms sound into spatial awareness with a precision that rivals, and in some cases exceeds, sight. This isn't science fiction or a fringe phenomenon. It's been observed, measured, and even taught using nothing but tongue clicks or finger snaps. Blind echolocators can detect walls, doorways, tree branches, parked cars, and even distinguish between textured surfaces like brick and metal. Not because they hear more acutely, but because their brains have learned to interpret sound in a way that most of us never imagined possible. The mechanics of echolocation begin simply. You emit a sound, it bounces off an object, and the returning echo carries information about distance, shape, and surface quality. But the true marvel isn't the physics. It's the neuroplasticity that allows the brain's visual cortex to be recruited for auditory processing. In expert echolocators, parts of the brain that in sighted people would process light and edges, instead, light up in response to echo patterns. In essence, their brain rewires itself, not to restore vision, but to repurpose the architecture of vision for a new form of sensing. Echolocation in blind humans has been formally studied since at least the 1950s, but public awareness remained limited, perhaps because it challenges one of our most basic assumptions, that vision is irreplaceable. Yet individuals like Daniel Kish, who lost his eyes in infancy, have demonstrated remarkable spatial abilities using echolocation. He can ride a bicycle in city streets, hike alone in the wilderness, or navigate unfamiliar buildings without a cane, guided not by sight, but by clicks and the spatial echoes they produce. In brain imaging studies, Daniel's primary visual cortex, normally silent in the blind, is active when he echolocates, suggesting that his brain sees the echoes. This phenomenon is a powerful reminder that the senses are not fixed, but adaptable. When one input channel is removed, the brain doesn't shut down the corresponding region. It waits, it listens, it finds new signals to fill the void. But how does the brain interpret these echoes? The tongue click, typically used by echolocators, is a sharp, brief, high-frequency sound that reflects efficiently off nearby objects. When the echo returns, it carries with it timing cues, how fast it bounced back, intensity, how loud it remains, and frequency distortion, how the pitch changed due to surface or angle over time with practice. The brain begins to extract spatial information from this data. The mind creates a map, not of images, but of acoustic landscapes, depth, contour, proximity. And this is more than theory in blind echolocators. Studies show that they can differentiate objects as small as a tennis ball or as subtle as an open door versus a closed one. Some can even estimate material, determining whether a surface is soft, like cloth, or hard like metal, based on the texture of the returning sound. Importantly, echolocation doesn't just happen in passive listening. It requires active emission and interpretation, a conversation between the self and the world, mediated entirely through vibration. What's even more remarkable is that this ability is teachable. Sighted individuals can learn basic echolocation in as little as a few weeks, navigating through hallways, blindfolded, locating objects by clicking. But in blind individuals who rely on it daily, the skill becomes second nature, a seamless extension of the self. In fact, advanced echolocators report experiencing a sense of shape and distance so vividly that they often forget they are using sound. Some even describe spatial awareness as a kind of mental image. A landscape felt more than seen. This challenges conventional definitions of perception. It suggests that seeing, in its deepest sense, may not require eyes at all. Only structured input, attention, and interpretation. The implications for neuroscience are profound. Echolocation offers a living model of how the brain can restructure itself in response to environmental demands. It also illustrates the concept of sensory substitution, the brain's ability to reroute tasks from one sensory channel to another. In experiments, even sighted individuals using blindfolds for extended periods begin to show activation in the visual cortex when interpreting tactile or auditory signals. This flexibility offers hope for brain-machine interfaces, prosthetics, and rehabilitation therapies, showing that the brain is not a collection of static modules, but a fluid and responsive network, constantly rewriting its code based on available inputs. There's also a philosophical resonance here. If perception is this adaptable, then our experience of reality is far more subjective and constructed than we assume. What you see is not the world itself, but the output of a sensory process. And that process can change dramatically, not just in function, but in architecture. If someone without eyes can perceive a tree, a bicycle rack, or a hallway using sound, and do so with grace, speed, and safety, then what is seeing really made of? Is it photons, or is it understanding? Perhaps perception isn't a passive reception of input, but an active, dynamic interpretation built through experience and reinforced through use. Echolocation becomes not just a compensation for blindness, but a revelation that human consciousness is not limited by the 5 classic senses, but shaped by the brain's ability to translate, reassign, and expand them. In a world dominated by visual information, from screens to signs to facial expressions, the idea that one can build a rich and detailed mental map entirely through echo is humbling. It reminds us that our perspective is just one of many possible versions of reality. Blind echolocators are not lacking something. They are operating on a different sensory algorithm, one that's equally valid, equally sophisticated, and in some ways even more impressive. They demonstrate that we are not trapped by our biology, but empowered by it, that within the constraints of the human body lies a boundless adaptability waiting to be uncovered. So the next time you hear a sound bounce off a wall, a footstep echo in a corridor, or your own voice shift slightly in a closed room, remember that sound is more than noise. It's a carrier of space, shape, and meaning. And with enough practice, enough attention, and a little curiosity, your brain could learn to see through it too. Not by sight, but by echo. The world, it turns out, has more than one way of revealing itself. And your mind has more than one way to understand it. Pain is an interpretation, not a signal. Somewhere deep within you, pain doesn't begin with an injury. It begins with a decision. A decision not made consciously, not one you can control, but one made silently by your nervous system as it interprets the flood of signals coursing through your body. This might sound strange at first. We're taught that pain is a direct result of damage, that if you touch something sharp, you feel the sharpness. If you sprain your ankle, you feel the twist. But in reality, pain is not a simple reflex or a mechanical consequence. Pain is a judgment, an interpretation built by your brain using context, expectation, memory, attention, and emotion. And it is entirely possible to be injured and feel nothing, or to feel agony without any physical cause at all. The sensation we call pain is not transmitted from your skin or muscles to your brain like a message in a bottle. Instead, your body sends raw data, and your brain decides whether that data warrants suffering. That means pain is not what happens to you. It's what your brain believes is happening to you. To understand this, we must look at the system itself. The body has nociceptors, specialized nerve endings, that detect potentially harmful stimuli such as pressure, heat, or tissue damage. These nociceptors send signals to the spinal cord and then to the brain. But, and this is key, the signal they send is not pain. It is merely information. Something sharp touched the skin. Temperature is rising. Tissue stress is increasing. The brain receives this information and evaluates it. Is it dangerous? Has this happened before? Is there an emotional context? Are you stressed, afraid, distracted, expecting pain? Only then does the brain generate the subjective experience we call pain. In fact, under the right conditions, the brain can suppress pain entirely. This is known as stress. Induced analgesia, and it's the reason soldiers can be shot in battle and keep running, or why athletes can tear ligaments and keep competing. Their brains prioritize survival over suffering, and so they dampen or eliminate pain signals. Conversely, the brain can create pain out of nothing, such as in phantom limb syndrome, where people feel stabbing, burning pain in a limb that no longer exists. These aren't psychosomatic illusions. They are the real experience of pain generated by the brain itself. Even more fascinating is the placebo effect, in which pain is reduced simply because a person believes they've been treated. Give someone a sugar pill and tell them it's morphine, and their brain releases real endorphins, natural opioids that reduce pain perception. Brain scans show decreased activity in pain-related regions, and sometimes even changes in spinal cord signaling. The expectation of relief becomes relief. But there's a darker mirror to this. The nocebo effect, where believing that something will hurt makes it hurt more. A harmless cream can cause burning if the user is told it might. Pain isn't just a biological response. It's woven into meaning, into stories we tell ourselves about what's happening to our body. Your past experiences, your emotional state, even the way doctors speak to you, can all shape how much something hurts. It's not weakness or exaggeration. It's the brain doing what it's designed to do, protect you by interpreting threat. The more threat it senses, the more pain it produces. And the context doesn't have to be dramatic to influence pain. A study showed that red-colored pills are perceived as stronger than blue ones, that the price of a treatment affects how well it works. Expensive placebos reduce more pain than cheap ones. In one remarkable experiment, participants were burned with the same temperature of heat, but when the stimulus was paired with different visual cues, a red light versus a blue light, the red light trials were rated as significantly more painful, even though the temperature was identical. This tells us that your brain doesn't simply receive pain. It constructs it, integrating sensory input with meaning, context, and prediction. And because pain is constructed, it can be deconstructed. Not easily, not by willpower alone, but through techniques that alter interpretation, cognitive behavioral therapy, mindfulness, expectation training, and even certain forms of hypnosis. One of the most powerful demonstrations of this comes from the phenomenon of mirror therapy, often used to treat phantom limb pain. A person with an amputated arm sits in front of a mirror, which reflects their intact arm in place of the missing one. By moving the visible hand and watching its reflection, they can trick the brain into believing the missing limb is moving. And often, this reduces or eliminates the phantom pain. Why? Because the brain is deeply visual. and it uses sight to update its internal body map. When the map is corrected, the pain decreases. Again, we're reminded, pain is not just about nerves or injuries. It's about perception. And perception can be shaped, redirected, and even healed, not by denying the pain, but by changing the meaning of the signals the brain receives. This understanding is more than just neuroscience. It's deeply human. It means that when someone says they're in pain, even if doctors find no physical cause, that pain is still real. Their suffering is not invalid just because no injury is visible. In fact, chronic pain conditions like fibromyalgia, complex regional pain syndrome, or irritable bowel syndrome often show no clear tissue damage, yet produce intense and disabling pain. This isn't malingering. It's the brain's alarm system misfiring, stuck in a loop, overprotecting. Treatments that only address the body, pills, surgeries, often fail because the source of pain is interpretative, not purely mechanical. To truly treat pain, we must treat the meaning of pain, which includes listening, believing, and addressing the whole person, their history, fears, beliefs, environment, and emotional landscape. Pain then becomes a kind of story the brain tells the body, a narrative of threat and protection. And just like stories, it can be edited, not easily, not completely, but meaningfully. Some therapies focus on retraining the nervous system, helping patients move in ways that were once painful to show the brain those movements are now safe. Others work on reframing beliefs about the pain, reducing fear and anxiety that amplify the signal. Even small acts, a change in lighting, a comforting voice, a moment of calm, can reduce perceived pain by shifting the brain's sense of threat. The goal is not to ignore pain, but to understand how it's made, so it can be unmade. And in this, there is deep hope, because if pain is an interpretation, then new interpretations are possible. The suffering is real, but so is the capacity to change the way it's experienced. So the next time you feel pain, whether sharp or dull, fleeting or chronic, ask yourself, what else is your brain sensing? What context surrounds the hurt? What memory, fear, or expectation might be coloring the sensation? This doesn't mean the pain is just in your head. It means your head, your brain, your mind, your lived experience is an essential part of the pain itself. And that opens the door not just to better treatments, but to deeper empathy, more accurate understanding, and a profound truth. What hurts isn't always what's broken, and what's broken doesn't always hurt. Pain is a lens, not a lamp. It doesn't just reveal damage, it interprets it. And the more we understand that, the closer we come to healing. Eyes have a blind spot you never notice. What if I told you that right now, as you read this? No matter how wide open your eyes are, no matter how focused or alert, there's a hole in your vision, a literal gap in your sight where the world simply disappears. And you never notice. It's not a metaphor. It's not symbolic. You actually have a blind spot in each eye, a place on the retina where there are no photoreceptors, no rods or cones to catch light, no image being formed at all. And yet you go through your entire life as if your vision were smooth and unbroken. This isn't because you're seeing around it or ignoring it consciously. It's because your brain is fabricating what should be there, filling in the blank with its best guess, and then presenting it to you as if you saw it yourself. You are not seeing everything. You are being shown an edited version of the world, cleaned up, repaired, and delivered to your consciousness with gaps seamlessly patched. It raises a quietly disorienting question. How much of what you see is real, and how much is an illusion your brain has constructed, so you never notice what's missing? This phenomenon, known as the physiological blind spot, exists because of the optic disc, the place where the optic nerve connects to the retina. This spot is devoid of light, detecting cells, meaning it cannot receive any visual information. In each eye, it creates a blind zone roughly 5 to 7.5 degrees of your visual field, enough to fully obscure a thumb held at arm's length. And yet, unless someone specifically points it out or you perform a certain kind of test, you'll never realize it's there. Why? Because your brain doesn't let you. It fills in the gap using the surrounding colors, textures, and patterns. Not with actual information from the world, but with an educated guess, a projection, a perceptual illusion so convincing that you rarely doubt its completeness. This is not just clever, it's necessary, because if we walked around constantly aware of gaps in our sight, our ability to navigate the world would be deeply impaired. Instead, the brain opts for continuity over accuracy, smoothness over truth. There are countless experiments that reveal this blind spot. One of the most famous involves focusing one eye on a single point while slowly bringing a nearby object, like a dot or cross, into your peripheral vision. At just the right distance, the object vanishes, not fades, not dims, but disappears completely, swallowed by the blind spot. And then, as if by magic, it is replaced with the surrounding background. If the dot is on a patterned surface, the pattern will fill in the missing area. If the dot is on a colored field, the color will smear across it, hiding the absence. You aren't just missing part of the image, you're seeing something that was never there to begin with. Your perception is being forged, moment by moment, from a combination of direct input and silent fabrication. But here's where it gets even more interesting. The blind spot isn't the only thing your brain fills in. This mechanism, called perceptual completion, happens constantly across your senses. Your brain smooths over saccadic eye movements, the rapid jumps your eyes make multiple times, per second, so that you don't see the world as a jittery blur. It fills in color at the periphery of your vision, where cones are sparse. It even creates a stable image from two slightly different retinal perspectives, one from each eye, so that you perceive a single coherent world. Your experience of reality is not just constructed, it's curated, edited, cleaned up before you get to see it. And all this happens without your permission or your awareness. It's a kind of benevolent hallucination, designed not to deceive maliciously, but to help you function smoothly in a chaotic world. You are not so much perceiving the world as being presented with an illusion of continuity that your brain believes will serve you best. Now pause and think about what that means for trusting your senses. We grow up believing that seeing is believing, that vision is the most reliable, objective sense we have. But if even something as basic as your visual field contains built-in gaps that your mind has to patch with guesswork, then how much of what you know visually is just well-executed fiction? If your eyes can deceive you about what's absent, can they also deceive you about what's present? And the answer is yes. Not because your brain is flawed, but because it's trying to make sense of a chaotic world. With limited information, it extrapolates, it edits, it completes what is incomplete, not just visually, but emotionally, contextually, and narratively. The blind spot is a symbol of something far larger, the idea that our entire reality is filtered, smoothed, interpreted, and reconstructed by neural processes we cannot feel and do not control. In fact, the implications of the blind spot reach beyond neuroscience into philosophy and identity. Because if you can go your entire life with literal holes in your perception and never know it, because your mind covered for them so well, what else might you be missing? What emotional blind spots have you filled with comforting narratives? What social cues, patterns, or biases have you overlooked because your brain made assumptions on your behalf? The blind spot teaches us a quiet humility. We don't perceive reality as it is. We perceive what's useful, what's coherent, what allows us to function. It's not a flaw, it's a feature, but it's also a limitation. And recognizing that limitation can make us more curious, more open, and more compassionate toward the gaps in other people's perceptions too. So next time you look at the world, at a landscape, a face, a piece of art, a screen, remember that somewhere in that field of vision there is a piece you're not seeing, and yet your mind is telling you it's complete. Remember that every moment of clarity you experience is partially imagined, not fake, not false, but carefully stitched together from fragments. And in that stitching lies both a marvel and a mystery, the incredible power of the human brain to create wholeness from fragments, and the sobering truth that wholeness may be an illusion itself. The blind spot is not just in your eye, it's in your understanding of how fully you grasp the world. And noticing that truly noticing it might be the first time you finally see what you've been missing all along. Your body knows things before your mind. There's a moment you can't explain, a shiver before danger, a tension before the fall, a gut feeling before the lie is spoken. And though your conscious mind hasn't caught up, your body has already moved, already decided, already known. This uncanny sensation of your body reacting before you fully understand why is not superstition or metaphor. It's real, measurable, and deeply biological. You are not just a thinking mind riding inside a passive shell. You are a complex, predictive organism, wired to feel before it knows, to respond before it reasons, to react before it reflects. This gap between body and mind, between instinctive sensation and conscious realization, reveals something astonishing: that the intelligence within you is layered, and that the layer you think of as you is not always in control. In fact, by the time your brain becomes aware of many events, your body has already responded, adjusted, and sometimes even made a decision. It's a silent hierarchy, and your mind is not always the first to know. This phenomenon appears across systems, neurologically, emotionally, even socially. One of the most well-known examples comes from neuroscience: the readiness potential, a burst of neural activity in the motor cortex that occurs milliseconds before you become consciously aware that you've decided to move. In a famous series of experiments by Benjamin Libet, participants were asked to move a finger or wrist at a moment of their choosing, and to note when they felt they had made the decision. Astonishingly, brain activity indicating the movement began 350–400 milliseconds before participants reported consciously deciding to act. That is, your body decides to move before your mind believes it made the choice. More recent studies using fMRI have extended this window up to 7 seconds, showing that patterns of brain activity can predict which button you'll press before you think you've chosen. This doesn't mean free will doesn't exist, but it does suggest that consciousness is often a narrator, not an initiator, reporting after the fact what the body has already started to do. But it goes beyond movement. Your body anticipates emotional events too. In studies of galvanic skin response, which measures tiny changes in sweat gland activity, researchers found that participants' skin reacted to disturbing or exciting images before the images were shown. The studies were randomized, with images appearing unpredictably, and yet the body responded seconds early, as if preparing for what was coming. How? One explanation lies in predictive processing, the brain's constant attempt to model and anticipate future states based on prior experience. Your nervous system is not just passively reacting to input, it's actively predicting what's next and priming your body to respond before the evidence is fully in. Your gut tightens, your pupils dilate, your muscles brace, not because your mind knows, but because your body suspects. This is why you may flinch before a glass shatters, or feel a drop in your stomach before bad news is spoken, or sense danger in someone's tone long before their words catch up. Even in social situations, your body reads micro signals far faster than your conscious mind. In the blink of an eye, within 100 milliseconds, you can detect whether a face is angry or safe, whether a voice is tense or calm. Your mirror neuron system fires instantly, allowing you to simulate and feel into another person's emotion without thinking about it. This is why you sometimes feel awkward before you understand why, or sense that someone is lying before you catch the contradiction. Your body absorbs posture, prosody, pupil size, and motion, subconscious clues, and processes them faster than language ever could. These reactions don't come from magic or intuition. They come from embodied intelligence evolved over millions of years, honed for survival, and tuned to threat detection so precisely that your body flinches at shadows before your mind can name the shape. And the gut, that often dismissed source of hunches and instincts, turns out to be neurologically powerful. The enteric nervous system, often called the second brain, contains more than 100 million neurons, more than the spinal cord, and operates semi-independently of the central nervous system. It can regulate digestion, hormone release, immune function, and mood without your conscious input. It also communicates with the brain via the vagus nerve, sending signals upward from your internal state to influence how you think and feel. When you say you have a gut feeling, it's not just metaphor. Your gut is literally signaling your brain, shaping your decisions, influencing your behavior, and guiding your attention, often faster than cognition itself. Anxiety, for instance, can begin in the gut and travel upward, not the other way around. Hunger alters risk perception. Gut inflammation can alter emotional processing. The body does not follow the mind. The mind responds to the body. This disconnect, this temporal inversion of sensing before knowing, is why athletes talk about being in the zone, why musicians speak of playing without thinking, and why people in crises often act before they're aware of what they've done. These are not moments of luck. They're examples of the body's intelligence taking over, moving faster than reflection, bypassing the slow deliberation of thought in favor of the immediacy of trained, embodied action. Think of a firefighter catching a collapsing beam without conscious calculation, or a driver slamming the brakes before the mind processes the red light. In these moments, the body is not clumsy flesh waiting for orders. It is fast, smart, and predictive, and it keeps you alive by knowing what you haven't yet understood. The implications are humbling. Your mind, proud and narrative-driven, is not the king atop the tower it believes itself to be. It is a narrator, not a commander, interpreting signals from the body and constructing meaning after the fact. This doesn't diminish the value of conscious thought. It expands it, because once you realize that you are not a floating intellect trapped in a meat suit, but a whole-body intelligence distributed across organs, nerves, cells, and reflexes, you begin to trust other kinds of knowing, feelings, intuitions, sensations that speak not in words but in pulses, tightness, warmth, or unease. Your body is speaking, and often it speaks first. So the next time you feel something in your stomach before a decision, or you catch your breath before a sound, or your skin crawls before your mind can explain why, don't ignore it. That's you. That's your real intelligence. Not slower, not lower, but simply earlier. It is embodied neuroscience, and when you learn to listen to it, not blindly but attentively, you gain access to a deeper layer of awareness, one that doesn't just react to the world, but anticipates it. Your body is not behind your mind. In many ways, it's leading it, and all your mind needs to do is finally learn how to follow. Some people taste words. You've probably never tasted a name before, never felt the fizz of an F on your tongue or the bitterness of the number 4. But for some people, language isn't just heard or read, it's savored. It's a world where words have flavor, where syllables shimmer with texture, and where a sentence can feel like chewing on velvet or biting into metal. This isn't metaphor. It's a rare and real neurological phenomenon called lexical gustatory synesthesia, a condition where people quite literally taste words. And as strange as it may sound, this unusual blending of the senses opens a window into how deeply interconnected our brains truly are, and how the walls we think exist between hearing, tasting, seeing, and feeling are. The idea that hearing a name could trigger a sour flavor, or that days of the week might taste like burnt toast or ripe watermelon, might seem like poetic exaggeration. But to a synesthete, it's as involuntary as blinking or breathing. They are not imagining it. Their brain is wired in such a way that language physically activates the taste centers of the brain. And what this tells us isn't just something about rare brains. It tells us something about all of us. That perception is far more fluid, far less categorized, and far more constructed than we assume. The condition itself is extremely rare, possibly affecting only a few hundred people worldwide, and yet it has been rigorously studied in peer-reviewed neuroscience labs. Functional MRI scans reveal that when synesthetes hear or read specific words, their gustatory cortex, the region responsible for taste, lights up in measurable ways. This is not suggestion, not imagination, not placebo. It is brain activation that mirrors real taste perception. One documented case involves a woman who tastes bacon when hearing her friend's name, or mustard when reading specific verbs. For her, and others like her, language isn't processed in isolation. It's felt through the senses in unexpected ways. And what's more intriguing is that the associations are consistent. The same words trigger the same tastes for years, even decades. This is not randomness, it's a stable neural pattern, an automatic sensory echo between circuits that in most people remain separate. These connections are believed to form in early development, and some researchers suspect they may arise due to excessive pruning not happening in the infant brain. In other words, we may all be born with more interwoven senses, but only some retain that vivid overlap. This phenomenon is a subset of a broader category called synesthesia, in which stimulation of one sensory pathway automatically triggers another. Some people see numbers as colors. Others feel sound on their skin, and still others can sense shapes when listening to music. But lexical gustatory synesthesia stands out because it involves something deeply primal. Taste, unlike color or sound, which are processed externally and abstractly. Taste is visceral, tied to survival, memory, and emotion. To taste a word is to embody it, to ingest language in a way that bypasses metaphor entirely. And remarkably, most synesthetes don't find it disturbing. They find it natural. They've never known life without it. For them, Monday might taste like mince, Catherine might taste like ketchup. These aren't preferences, they're realities, and they're deeply personal. No two synesthetes report the same associations, which hints at a complex, individualized mapping of the brain's language-taste networks. Scientists studying synesthesia have found something even more profound. The boundaries between the senses may be more artificial than we thought. Our traditional model of the five senses, sight, hearing, taste, touch, and smell, is tidy but limited. In truth, the senses are interdependent and deeply contextual. When you eat food, for instance, you don't taste it with your tongue alone. Your nose, your memory, your attention, and even the color of the plate influence the experience. So when we hear about synesthetes tasting words, perhaps the more radical idea is not how strange they are, but how much they reveal about how strange we all are. Because even without synesthesia, you can likely recall moments when music felt warm, or sadness felt heavy, or someone's voice had a sharp edge. These are not accidents. They're echoes of a brain that's constantly blending input, trying to make sense of an overwhelmingly multisensory world. And there are clues that mild forms of synesthetic processing exist in many of us. Some studies show that even non-synesthetes unconsciously associate certain vowels with specific shapes or textures, a phenomenon known as the Buber-Fakiki effect. For example, when shown two shapes, one round and blobby, the other spiky and angular, people across cultures tend to call the round one Buber and the sharp one Kiki. Why? Because our brains link sound to shape in consistent ways, even if we're not aware of it. This cross-modal perception is foundational to language development, metaphor, and even memory. When you say someone has a sweet personality, or that a situation leaves a bad taste, you're using sensory overlap, not just as decoration, but as a natural extension of how the brain understands meaning. This also opens the door to fascinating applications. In experimental art, some creators have collaborated with synesthetes to create multi-sensory performances, pairing spoken word with matching flavors, turning poems into meals. In therapy, understanding synesthesia may help with sensory integration disorders or neurodiverse education. In marketing and design, companies have begun exploring how certain sounds influence flavor perception, because even without true synesthesia, our expectations shape our sensory experience. A high-pitched sound can make a drink taste sweeter. A certain word choice can change how bitter we perceive a food. This blurring of boundaries isn't just for the rare few. It's happening in all of us, all the time, in ways we rarely notice. So when you hear that some people taste words, don't think of them as broken or bizarre. Think of them as reminders that your brain is capable of more than strict boundaries and neat categories. You may not taste Tuesday or find garlic in the name George, but you do mix senses every day, in music, in metaphor, in memory. Synesthesia is not a glitch, it's a glimpse. A glimpse into a human mind that was never meant to be confined by just one sense at a time. A mind that beneath the surface may be far more fluid, colorful, and flavor. Rich than you've ever been told. Your nose never stops smelling. You may not notice it, but you are always breathing in the world. Not just air, but molecules, memories, moods, and invisible cues that drift past your awareness in silence, even as they shape your decisions, your emotions, and your sense of what feels real or safe or familiar. Because the truth is, your nose never stops smelling. Your brain just chooses not to tell you. This hidden sense, always humming beneath consciousness, is one of the most underestimated forces guiding your life. At every moment, whether you're awake, asleep, aware, or distracted, scent molecules are entering your nasal passages, landing on receptors in your olfactory epithelium, and sending electrical signals directly to your brain's limbic system, the same region that processes memory, fear, love, and instinct. But here's the strange part. Unlike your other senses, the olfactory system has no thalamic relay. That means smell bypasses the brain's usual gatekeeper and goes straight to the emotional core, a raw, unfiltered signal from the world, arriving without context or explanation. This might explain why smells can hit you like ghosts. A whiff of shampoo dragging you back to childhood, or the scent of old paper unlocking emotions you can't name. But what's even more fascinating is that most of the time, you don't notice any of it. Your brain, in a process called olfactory adaptation, simply stops reporting the smells that linger too long. It is not that the signal disappears. It is that your mind decides it's no longer worth your attention. In other words, your brain edits your reality in real time, quietly suppressing input from a sense that never shuts off. This might seem like a limitation, but it is actually a survival feature, a way for the brain to avoid sensory overload. Imagine if you smelled your own laundry detergent, skin oils, and indoor air with full intensity every second of every day. You'd be overwhelmed. Instead, your brain adapts. It normalizes constant scents to clear space for new ones. That's why you notice the smell of someone's perfume when they walk in, but stop noticing it 5 minutes later. Your olfactory system is like a vigilant security guard that doesn't shout unless something changes, and that something could be vital. The scent of smoke, or spoiled food, or an unfamiliar human nearby. Smell is your oldest sense, evolutionarily speaking, and it's wired to detect not just pleasure but danger. Long before humans had language, we had smell, and our ancestors relied on it to navigate the world, to tell food from poison, friend from foe, safety from threat. But in the modern world, where artificial fragrances, sterile environments, and mental busyness crowd the mind, we've learned to ignore our nose, or worse, distrust it. We associate smell with the primitive, the animal, the unconscious, not realizing that those very qualities are what make it so powerful. Your nose is a historian, a danger detector, a silent emotional compass, always on, always processing, always waiting for your awareness to catch up. Even more astonishing is the role that smell plays in shaping your social and psychological life. Studies have shown that humans can detect emotions like fear or disgust through scent alone, even if they're unaware of doing so. In one experiment, researchers collected sweat samples from people experiencing fear, and when other participants inhaled those samples, without knowing what they were smelling, their own bodies showed signs of fear response. Their heart rates changed, their facial expressions subtly shifted, and brain scans lit up in the amygdala, the region associated with threat detection. This means your nose may be responding to other people's emotions before your mind has any idea what's happening. Smell is also deeply tied to attraction. We tend to prefer the scent of people whose immune system genetics differ from our own, a mechanism thought to promote healthier offspring. This subconscious compatibility, often referred to as MHC compatibility, means that part of who you're drawn to might have more to do with biochemistry than personality. And yet we rarely acknowledge this, because scent, while constant, is quiet. It shapes the background music of perception, setting the emotional tone without demanding the spotlight. But make no mistake, it is always there. Perhaps most hauntingly, smell is the last sense to fade before death, and the first to form before birth. Newborns recognize their mother's scent within days. Alzheimer's patients often lose their sense of smell years before cognitive symptoms emerge. In fact, the olfactory bulb is one of the first areas affected by neurodegenerative diseases, making smell loss an early and underused diagnostic signal. Your sense of smell is not separate from who you are. It is a portal to memory, identity, and awareness. It's why smelling an old lover's cologne can bring you to tears. Why the scent of rain can stir nostalgia. Why the sterile smell of hospitals can fill you with dread, even before a diagnosis is spoken. You don't just remember smells, smells remember you. They are encoded with time, emotion, and context, stored in the folds of your brain that live beneath language. This is why scent-triggered memories often arrive whole, vivid, and raw, like stepping back into a moment you didn't know you missed. But here's the twist. Most of your scent experience is actively ignored. This is not a flaw, it's a function. Your brain decides what you notice. It filters, prioritizes, and silences, which means your experience of the world is not just limited by biology, but by attention. What else are you overlooking? Not because it's absent, but because your mind has decided not to show you. The truth is, perception is a choice, often made for you, without your consent. The brain prunes and edits constantly, and your nose is perhaps the most striking example of this quiet censorship. Yet, if you really pause, and inhale with attention, you can sometimes catch it in the act. The faint trace of citrus on your fingers after peeling an orange, the dusty scent of old books in a forgotten room, the earthy tinge of wet soil after rain. These are not trivial. They are fragments of presence, ways the world speaks to you without words. And in listening to them, in noticing what you were taught to ignore, you reclaim part of your awareness, and maybe part of yourself. Scent alters morality. You might believe that your moral compass is a fixed internal force, a product of values, reasoning, upbringing, and conscious reflection. But what if I told you that something as subtle as the smell of citrus in a room could make you more likely to act ethically, more generous, or even more judgmental? That the presence of a barely noticeable scent could sway your decisions on fairness, punishment, or compassion, without your awareness, without your consent? It sounds impossible, even absurd, that something so ephemeral as an airborne molecule could tinker with the weighty gears of morality. And yet, that's exactly what studies in the fields of social psychology and olfactory neuroscience have begun to uncover. Your sense of right and wrong is not as insulated from your environment as you think. It can be nudged, bent, and sometimes even reversed by the silent influence of smell. In a series of now famous experiments, participants asked to complete questionnaires in rooms scented with cleanliness. Associated aromas like citrus or pine were significantly more likely to behave honestly, to donate to charity, or to judge others more harshly for ethical violations. Meanwhile, exposure to unpleasant or body-related smells, like the faint scent of sweat, decay, or even flatulence, triggered stronger moral disgust responses, more conservative social attitudes, and a heightened sense of danger or contamination. These shifts weren't conscious or rationalized. The participants didn't report feeling more moral or judgmental. Their behavior simply changed. Their environment whispered into their emotions, and their emotions quietly rebalanced the scale of justice in their minds. To understand how scent can alter something as seemingly abstract and complex as morality, you need to know something strange about how your brain handles smell. Unlike vision or sound, which pass through a sort of cortical checkpoint, the thalamus, before reaching the emotional centers of the brain, olfactory input takes a shortcut, connecting directly to the amygdala and orbitofrontal cortex, areas deeply involved in emotional processing, decision making, and social judgment. This direct path makes scent uniquely powerful. It doesn't wait for your approval to change how you feel. It bypasses logic and walks straight into the emotional architecture of your experience, planting suggestions not with words, but with mood. And morality, though it often feels rational and deliberate, is rooted in emotion more than most of us are comfortable admitting. The revulsion you feel at a lie, the compassion stirred by a child in distress, the anger at a perceived injustice, these aren't abstract concepts. They're emotional states, shaped by hormones, memories, and the sensory context in which they arise. If smell can color your emotions, it can also tint your morality, and it does so constantly, quietly, and with more influence than you think. In one study, participants exposed to a room infused with a light citrus scent were not only more likely to clean up after themselves, but were also more prone to donate money when asked to help others, as if the cleanliness smell created a subtle moral clarity. In another, subjects who were subliminally exposed to unpleasant odors rated various moral transgressions, like lying, cheating, or incest, as significantly more wrong than those in neutral, smelling environments. The smells weren't strong. They were barely noticed, but the judgments shifted. These experiments suggest that your brain uses olfactory cues as a kind of moral context filter, aligning behavior with the emotional tone set by the environment. It's not just about whether something is right or wrong, it's about how your body feels in the moment you make the judgment. And smell, by altering that feeling, changes the way you weigh decisions. You might think you are being fair, objective, and clear-headed, but the scent of antiseptic or sweat, or even warm cookies in the air, might be pushing your sense of justice in one direction or another. Even more unsettling is the implication this has on institutions where moral decisions are made. Imagine a courtroom where the scent of cleaning products makes jurors more likely to convict, or a hospital where a faint antiseptic smell makes patients more submissive and deferential to authority, or a schoolroom where the comforting scent of baked goods influences teachers to grade more leniently. These aren't science fiction scenarios. They're extensions of what research is already suggesting, that your moral decisions are partially situationally constructed, influenced by sensory cues you barely register. The ethical implications are enormous. If your environment can subtly alter your moral responses, then the idea of consistent moral character becomes harder to defend. Are you the same, you in every room, or are you, at least partially, a product of the air you're breathing? And what about long-term exposure to specific scent environments? Could your moral development be affected by the smellscape of your childhood? If you grew up in a home that always smelled of bleach and soap, did that subtly reinforce values around cleanliness, order, or rigidity? If you were raised in a house filled with the scent of cooking, spices, and earth, did that embed a deeper association between comfort, nourishment, and care? We already know that memory and emotion are tightly interwoven with smell. But what if ethics is too? What if your moral framework is stitched together, not just by what you were taught, but by what you inhaled while learning it? This doesn't mean you have no agency, but it does mean that your ethical radar isn't floating in some isolated philosophical bubble. It's grounded in your body, and that body is porous. Scent enters without resistance. And once inside, it shifts the levers of emotion that guide your actions and judgments. This isn't manipulation, it's biology. It's the architecture of your brain responding to the signals evolution taught it to read. The disgust response you feel when someone violates a moral norm, that response shares its neurological substrate with the disgust you feel from spoiled food, the same circuit fires. That's why morality and purity are so closely linked in language and feeling. We speak of clean money, dirty lies, and rotten behavior, because the brain literally processes them together, and scent is the bridge. So the next time you make a moral decision, ask yourself, how much of that choice came from you, and how much from the invisible molecules around you? What if you are not just a mind thinking in a vacuum, but a nose swimming in signals, constantly rebalancing the scales of right and wrong based on subtle sensory context? This isn't to undermine ethics, it's to expand it. To recognize that being human means being influenced, and that part of maturity is learning to notice those influences without being ruled by them. Scent alters morality, not because you are weak, but because you are alive, because you're built to feel first and reason later. And perhaps the most moral thing you can do is to admit that truth, to question your instincts, and to remember, sometimes, even the air has an opinion. Temperature affects trust. You probably think of warmth and cold as physical sensations. Thermal measurements your body interprets through contact, wind, or ambient air. But what if temperature wasn't just something you felt on your skin, but something that quietly shaped how much you trust another person, how open you are to vulnerability, or how willing you are to see the best in someone you've just met? What if a cup of hot coffee could make you more generous in judgment, more forgiving in spirit, more inclined to believe that someone is honest? What if sitting in a chilly room could make you more skeptical, more guarded, more emotionally distant without you realizing why? These aren't metaphors. These are real effects, measured in labs, repeated across cultures, and so consistent that they suggest something deeply embedded in our psychology. Your sense of social warmth is thermally encoded, and it begins long before you ever think of it. Scientists have long suspected that metaphors like warm, hearted, cold-blooded, or a warm smile weren't just linguistic accidents. They reflect the way the human brain maps physical sensations onto social experience. In other words, your perception of someone's kindness, honesty, or approachability is linked to the same neural networks that process literal heat. The anterior insula, the brain region involved in integrating bodily sensations and emotions, doesn't separate a warm room from a warm hug. And research from Yale and other institutions has shown that even a minor manipulation in physical temperature, like holding a warm drink instead of a cold one, can increase interpersonal trust. In one famous experiment, participants who held a warm cup of coffee rated a fictional person as more generous and caring than those who held iced coffee. They didn't notice the influence. They just felt different and thought it was their own judgment. But it wasn't. It was temperature doing the whispering. The reason for this strange psychological link may lie in how human bonding evolved. In early life, warmth is survival. An infant associates the presence of caregivers, food, safety, touch, love, with literal body heat. Warmth means protection. Cold, by contrast, signals absence, distance, threat. These early associations don't just fade with age. They form the foundation of attachment. As adults, we may no longer need to be swaddled to survive. But our brains still equate physical warmth with social closeness, emotional safety, and trustworthiness. When you meet someone new and feel an instinctive liking, your body is already registering subtle cues, their tone, expression, posture, and yes, their temperature. If they are warm to the touch, or if the environment around you is comfortable and cozy, you are more likely to extend the benefit of the doubt. But if they feel cold, or the space you're in is physically chilly, your brain tightens, contracts, becomes more alert, more critical. You retreat slightly, emotionally, even if you don't understand why. This link between temperature and trust isn't limited to personal interactions. It influences negotiations, group dynamics, therapy sessions, and even courtroom judgments. In a study on jury behavior, warmer rooms led to slightly more lenient sentences, while colder ones increased punitive instincts. Therapists have noted that clients tend to open up more readily in physically warm settings, and employers who conduct interviews in warmer offices often rate candidates as more competent and socially skilled. In virtual interactions, where body heat can't be conveyed, people instinctively use visual cues like lighting, color tones, or background ambience to simulate warmth. And you trust them more if their environment looks warm. Even in architecture, spaces designed with warm colors, soft lighting, and cozy textures invite longer conversations and deeper connections. Your perception of another's character is not sealed in logic. It is stirred gently by temperature, by comfort, by the primal association between body heat and emotional safety. But the relationship also goes the other way. Feeling socially rejected, being left out in the cold, quite literally causes people to perceive ambient temperature as lower. In one experiment, participants who recalled a time of deep social rejection were more likely to estimate a room as cold and to prefer warm food or drink. Loneliness makes you feel colder, and that coldness makes you trust less, share less, connect less, creating a cycle that's difficult to break. Conversely, acts of kindness, touch, and shared laughter can raise not only your emotional temperature, but your physical sensation of warmth. This bidirectional loop between thermal and social experience may be one of the oldest survival systems our species ever developed. Warmth as life, warmth as connection, warmth as trust. So what does this mean for how we live? It means that trust isn't just about facts and consistency. It's about feeling safe. And safety begins in the body. If you want to have better conversations, build stronger bonds, or resolve conflict, start with warmth. Not just metaphorically, but literally. Offer tea, turn up the heat. Sit closer, bring blankets. Create an environment where the nervous system can relax. Because when the body feels safe, the mind opens. And when the mind opens, trust can grow. It's care. It's awareness of how humans actually work. In a world that often feels emotionally cold, where headlines shout, screens glow blue, and people retreat behind sarcasm and skepticism, rediscovering the power of warmth may be the first step toward a deeper kind of empathy. When you feel distant from someone, ask, is it really because they're untrustworthy? Or is it that your body isn't safe enough to feel otherwise? Could a change in temperature shift your entire judgment? Could it open the door to understanding? You are not a machine making rational calculations in a vacuum. You are a living body, interpreting every moment through nerves, skin, and sensation. Temperature is not just weather, it's context. It shapes who you trust, what you believe, how you judge. And perhaps the most human thing of all is realizing that to build a more trustworthy world, sometimes all we need is to make it just a little warmer. The mind fills in missing sensory data. There's a strange comfort in believing that what you see, hear, touch, smell, and taste is the whole truth. That your senses are 5 faithful messengers, delivering a complete and accurate map of the outside world. But what if that map is only a sketch, and your brain is constantly filling in the blank spaces without telling you? What if reality, as you experience it, is a clever reconstruction, a seamless illusion stitched together by a mind that hates uncertainty? You think you see everything in front of you, but you don't. You see fragments, samples, data points, and then your brain fills in the rest. That's not failure, that's design. It's how you survive. But once you understand this, once you really grasp how much of your daily perception is an act of unconscious completion, you'll start to question every assumption you've ever made about what's real, and more unsettlingly, what might be missing. Your senses don't record like a camera, they sample. Your eyes make rapid jumps, called saccades, that scan just parts of a scene. Your ears receive a blend of frequencies and masks certain sounds. Your skin registers only specific pressures and temperatures. Even your tongue has blind spots. The raw data that reaches your brain is sparse. noisy, incomplete. Yet what you experience is rich, fluid, and continuous. That's because your brain is filling in the blanks constantly. It guesses what should be there. It smooths over inconsistencies. It invents continuity where there's none. And you rarely notice. For example, your eyes have a blind spot where the optic nerve meets the retina, a hole in your vision with zero information, but your brain paints it over so perfectly, you've gone your whole life without seeing it. In a sense, you've never seen anything completely, only what your brain has decided to show you. This phenomenon, known broadly as perceptual completion, extends far beyond the visual. When you hear someone speak in a noisy room and still understand their sentence, your mind is patching in the missing syllables. When you feel your phone vibrate in your pocket, and it didn't, that's your tactile system misfiring based on prediction. When you taste chicken in a vegan substitute, or hear your name in a distant murmur, your senses aren't lying. They're interpreting, based on memory and context. Your mind is always filling in the blanks with what it expects. And expectations are powerful. In an experiment called the phonemic restoration effect, listeners heard a sentence where one word was interrupted by a cough. Yet nearly all of them reported hearing the full word. Their brain had edited out the interruption and replaced it with what should have been there. This is not passive sensing, this is active construction. Your reality is built, not received. But here's where it gets even stranger. Your brain doesn't just fill in the missing. Sometimes it creates what was never there. Optical illusions are a famous example. Take the Kinesa triangle. 3 Pac-Man shapes arranged, so your brain perceives a triangle that doesn't exist. Or the blind spot test, where a dot disappears and your brain fills the space with background. This happens because your brain is biased toward coherence. Gaps are uncomfortable. Discontinuity is suspicious. Your nervous system has evolved to prioritize a believable world over a precise one. It would rather invent than admit ignorance. In this way, perception is more like storytelling than measurement. You are the audience of a brain constantly editing its own movie, and you trust every frame. This tendency also explains why eyewitness testimony is so unreliable, why people remember things that didn't happen, and why 2 people can walk through the same room and describe entirely different experiences. Their minds have filled in different blanks based on different expectations, fears, memories, and beliefs. Reality is not a shared photograph. It's a collage of reconstructions. And we rarely agree on the missing pieces. In one sense, this is terrifying. You cannot fully trust your own experience. But in another, it's liberating. Because if your perception is a construction, then awareness of that construction gives you power. You can begin to ask, what's being filled in for me, and why? What assumptions shape what I see? What if I slowed down, questioned, opened space for uncertainty? Would I perceive differently? Even in science, this principle holds. Instruments don't give perfect data. Scientists interpret signals, filter noise, complete patterns. Artificial intelligence learns by training on missing data, predicting what should be there. Artists know this too. The most evocative works are often those that leave something out, inviting your mind to participate. In music, silence is as important as sound. In literature, suggestion moves more than detail. The mind craves involvement. It wants to co-create the world it sees, and that co-creation is happening every moment, even now as you read these words. Your brain is guessing the next phrase, filling gaps in grammar, smoothing over transitions you don't consciously process. So what's the lesson? It's not that you're hallucinating life. It's that life is always a blend of what is and what's guessed. That's not a flaw. That's how consciousness works. But it means that humility is crucial. It means that certainty is suspect. The next time you think you know what someone said or saw exactly what happened, pause. Ask yourself, is this complete? Or is my mind protecting me from the discomfort of a blank spot? You might be surprised by what you find, because sometimes the truth lives not in what is present, but in what's missing. And in the silent act of filling it in, your brain reveals more about you than about the world. Some feel touch in mirror reflections. You wouldn't expect your body to react to something that's not real. And yet, in front of a mirror, some people feel a touch that never happened. A sensation that doesn't come from the skin but still tingles with a strange reality, as if the boundary between reflection and experience had momentarily dissolved. This phenomenon, both eerie and deeply fascinating, opens a window into the construction of perception itself. How your mind, in its constant effort to make sense of the world, sometimes confuses what is seen with what is felt. And for those who experience mirror touch synesthesia, the line between observation and sensation is not merely blurred, it's inverted, entangled, crossed. They watch someone's arm being stroked and feel it on their own. The mirror becomes not a surface, but a portal. And what this tells us, more than any single neurological study, is that your brain isn't a passive recorder of touch. It's a prediction machine, a mapper of other minds, a simulator of flesh that doesn't belong to you. And it's more connected to the world outside your body than you've been taught to believe. Mirror touch synesthesia is rare, occurring in an estimated 1.6 to 2.5% of people. But it reveals something universal about how all humans process empathy, sensation, and the self. For most people, seeing someone touched doesn't provoke physical feelings, but it does activate some of the same brain regions involved in experiencing touch directly. These include the somatosensory cortex, responsible for mapping the body, and the mirror neuron system, which helps you understand others' actions and emotions. In mirror touch synesthetes, these systems are more cross-activated, leading the brain to misattribute observed sensations as personal ones. But even if you don't feel physical contact while watching someone else, your brain is still partially simulating that experience. You flinch when you see someone stub a toe. You shiver when a character walks barefoot through snow. You recoil at the sight of a needle piercing skin. These responses are not metaphorical. They are visceral simulations, triggered by neural circuits that cannot entirely distinguish between self and other. And this is not a bug in the system, it's a feature. It's how empathy evolved. But mirror touch synesthesia pushes this simulation to the extreme. In MRI scans, the brains of people with this condition show hyperactivity in tactile processing areas. When they observe others being touched, their body maps are overly permeable, as if the borders of their physical identity are less well defined. Some researchers speculate that this heightened mirroring might be linked to increased emotional sensitivity, or even difficulties with social boundaries. Others believe it offers insight into how we build the concept of self in the first place. After all, babies learn about their own bodies by observing others. They mimic facial expressions, reach toward reflected limbs, and slowly develop a sense of where they end and others begin. But that boundary is always, in a way, artificial, maintained by attention, habit, and convention. Mirror touch synesthetes simply live on the more porous edge of that line. The implications of this are profound. If observing another person's experience can generate real sensation in your own body, then your nervous system is not isolated, it's socially entangled. This doesn't just apply to touch. Studies have shown that seeing someone else in pain can activate your anterior cingulate cortex, a brain region associated with the emotional dimension of pain. This is why empathy can be exhausting, why caregiving or witnessing suffering can feel like being hurt yourself. Your body reacts as if it is happening to you, because, on some level, your brain believes it is. Mirror touch synesthesia is just a more transparent version of this shared sensitivity. It is empathy written in nerve signals instead of words. Even more strangely, the rubber hand illusion demonstrates how easily the brain can be tricked into remapping touch. In this experiment, a rubber hand is placed in front of you while your real hand is hidden. If both hands are stroked in sync, people begin to feel that the rubber hand is their own. Their brain adopts it into the body map. And if the rubber hand is threatened, say, with a hammer, they recoil. Heart rate rising, stress signals firing. This isn't mirror touch synesthesia, but it uses the same principles: visual input overriding physical truth. It shows that the brain's map of the body is negotiable, that what you feel can be modified by what you see, and that the unity of the self, the feeling that your body is yours and yours alone, is a cognitive construction. Powerful, yes, but flexible, fragile. This brings us back to the mirror, not just as a reflective surface, but as a metaphor for how we perceive others and ourselves. When someone experiences mirror, touch synesthesia, they become a kind of emotional mirror, reflecting others' experiences inwardly. But even those without this condition can learn from it, because it reveals the truth about connection, that we are not separate entities bumping into one another, but intertwined systems of perception, feeling, and interpretation. When you hold someone's hand, when you hug a friend, when you comfort a crying child, your brain is not just reading signals. So the next time you see someone wince, flinch, or smile with genuine relief, ask yourself, what do you feel in your own body? Can you trace the subtle ways your mind absorbs the lives of others? And can you accept that what you consider, you might be more open, permeable, and shared than you ever imagined? Because in the quiet spaces between sight and sensation, between body and reflection, lies a truth we often overlook, that to be human is to echo, to reflect not just light, but emotion, touch, and experience. In a nervous system built to feel not just for itself, but for all it sees, your pupils react to ideas, not just light. You might think your pupils only shrink or expand in response to light, that they open wide in darkness and contract in brightness like tiny camera lenses. But hidden beneath this automatic dance lies a far stranger truth. Your pupils also respond to thoughts, to ideas, to imagination itself, as if your mind had a shadow that casts itself not on walls, but into your eyes. The diameter of your pupils shifts not only when you enter a dark room or stare at the sun, but also when you solve a math problem, hear a lie, make a decision, feel attraction, or hold an abstract idea in your mind for more than a moment. Your pupils, quite literally, reflect what you're thinking, not metaphorically, but physiologically. They dilate when you're mentally engaged, when your brain is working harder, when you're surprised, aroused, deceived, or even when you're just trying to remember something vividly. And this simple biological response, a subtle widening or shrinking of a dark circle, reveals something astonishing, that your thoughts don't stay trapped in your head. They ripple out into your body. They leave footprints, micro signatures, quiet tremors that science can now measure. And perhaps one day read, this phenomenon is known as the task, evoked pupillary response, and its roots go deep into the autonomic nervous system. Unlike muscles you can control, your pupils are governed by the sympathetic and parasympathetic branches, the same system that governs your heart rate, digestion, and fight or flight reflexes. When your brain is confronted with cognitive load, a tough problem, a complex memory, a sudden realization, the locus coeruleus in your brainstem releases norepinephrine, a neurochemical linked to arousal, attention, and mental effort. That norepinephrine surge tells the iris to dilate, increasing pupil size ever so slightly. You can't feel it, you don't control it. But it happens every time your mind wakes up. It's as if your eyes gasp open to let in more, not just of the world, but of thought itself. You are a creature whose ideas have weight, and your pupils are the scale that registers them. And this is where the story gets even more curious. Because pupil dilation doesn't just reflect effort, it also mirrors emotion. When people look at images of people they love, or even just think about someone they're romantically attracted to, their pupils dilate. The same happens when viewing emotionally charged imagery, regardless of whether it is joyful or disturbing. This tells us that the pupil is not simply reacting to visual stimuli, but to emotional salience, to meaning. Your eyes widen when something matters. They expand for beauty, for fear, for connection. And in turn, other people read your pupils without even knowing it. In one study, When participants were shown identical faces, but with slightly dilated pupils, they consistently rated those faces as more attractive and more trustworthy. Your pupils aren't just reacting to the world, they're participating in it, shaping how you're perceived, how you connect, how you are read and felt and known. Even more fascinating, the link between pupil size and deception has become a tool in lie detection research. When someone tells a lie, especially one that requires cognitive effort to construct or maintain, their pupils tend to dilate ever so slightly but consistently. This isn't about guilt necessarily, but about the mental load of keeping two realities straight, the truth and the fiction. In that moment, the brain has to juggle conflict, narrative control, and emotional management, and the eyes give it away. It's the body betraying the mask, not through shaky voices or sweaty palms, but through a flicker in the eye's aperture. And this raises deeper questions. If thoughts leave traces, if the body cannot help but speak them, then how separate is the mind from the flesh? Is there such a thing as a truly private thought if your pupils betray you to the world? What's even more compelling is how these unconscious pupil responses feed into a feedback loop. When you see someone with dilated pupils, your own may dilate in response, a kind of empathetic mirroring that enhances social connection. In this way, pupil size becomes a silent dialogue, a physiological language layered beneath words, tone, and gesture. You're having conversations with your eyes that you don't even know about. Conversations of trust, of curiosity, of shared excitement, or veiled suspicion. In one study, participants unknowingly mimicked the pupil size of faces they were shown. Larger pupils led to larger pupil responses in the viewer, suggesting that human connection operates on channels so subtle we are blind to their presence, but not to their effect. The next time you lock eyes with someone, you may be saying more than you think. There's also evidence that pupil dilation plays a role in moral decision-making. When participants were asked to choose between morally difficult options, such as harming one person to save many, their pupils dilated during moments of high internal conflict, even if they didn't express uncertainty aloud. It's as if the pupil registers the weight of consequence before the conscious mind has settled on an answer. It feels, silently, what the heart hasn't yet named. This opens doors to the study of neuroethics, to using physiological signals not just to understand cognition, but to map morality. Can the eyes reveal what a person finds wrong, even when they deny it? Can pupil movement be a window, not only into the mind, but into the soul? But perhaps most beautifully, your pupils dilate in imagination, not just to reality, but to mental imagery. Think of a bright light, or a dark cave, or the memory of someone smiling, and your pupils will subtly shift as if those visions were real. This shows that the boundary between perception and imagination is not fixed. Your brain doesn't treat mental pictures and real sights so differently. When you dream, your pupils remain still, but in lucid dreaming, where awareness returns, pupil-like behavior may emerge again, as if your eyes were responding to a world that doesn't exist. The mind creates a world, the eyes follow. And that might be the most profound lesson of all, that your biology listens not just to the environment, but to your inner life. So when you next look into the mirror and see your pupils flare in shadow, remember that they are not just sensors, they are storytellers. They reveal what engages you, what moves you, what stirs beneath the surface. They respond to logic and love, to fantasy and fear, to memory and meaning. They open, not only to light, but to wonder. And maybe, just maybe, they are a small biological proof that what you think, what you imagine, what you feel, what you know in your quietest self, is real enough to be seen. Not just by others, but by the body that contains you. Your pupils are windows, not just to the world, but to you. Your brain hears with memory too. You might think that hearing is simple. That sound enters your ears, travels through the auditory canal, vibrates your eardrum, and from there, your brain processes it like a tape recorder set to play. But in truth, you never actually hear the world exactly as it is. Instead, you hear a version of it shaped and sculpted by your memories, expectations, and past experiences. Because hearing is not a passive act of reception, but an active process of reconstruction, and what you perceive as sound is always a blend, some part vibration, some part imagination. Even before a note finishes playing or a voice finishes speaking, your brain has already begun predicting what it thinks it's about to hear. And this prediction colors everything that follows. That's why a song can hit differently, depending on your mood, or why an old voice message from someone you've lost can suddenly make the air around you feel thick. Because your brain is not just hearing, it's remembering, interpreting, and emotionally responding in real time. Studies in auditory neuroscience have shown that auditory cortex activity occurs even in the absence of sound, triggered purely by expectation or memory. In one experiment, participants were shown a silent video of someone playing a familiar instrument, and just watching the motion activated their auditory cortex, as if they were hearing the sound, because their brain expected the sound to be there, and memory filled it in. In music, this phenomenon is called audiation, the ability to hear music in your mind that isn't actually playing, and it's not limited to musicians. Every time you finish someone's sentence in your head before they say it, or hear the jingle that matches a commercial just from seeing the product, that's your auditory memory working behind the scenes, coloring the present with the past. And it goes even deeper. Your emotional associations with sound, like the comforting creak of the floorboard outside your childhood bedroom, or the terrifying ring of a hospital phone, are not just passive echoes. They shape how you interpret future sounds too. The brain uses these memory traces to decide what is meaningful, and what is noise, what is a warning, and what is warmth. And that decision can happen faster than conscious thought. In fact, the brain's primary auditory pathway shares strong connections with the limbic system, the emotional processing center, especially the amygdala and hippocampus, which are responsible for fear, pleasure, and long-term memory. That's why hearing a particular voice can make you feel safe or unsafe in an instant, or why the sound of sirens might trigger anxiety in someone who's been through trauma. Your ears may pick up the vibrations, but it's your memory that gives them meaning. Remarkably, even the absence of sound can be interpreted differently depending on context. A quiet room can feel peaceful or ominous, depending on what silence has meant to you in the past. This is why people who have experienced intense grief often find silence unbearable. It is not the lack of noise that haunts them, but the echoes of memory in the quiet. The soundscape of your life isn't just made of what happens outside of you. It's composed of every voice you've heard, every sound that mattered, every auditory detail that was once tied to emotion. That's also why certain accents can feel familiar, or why the rhythm of someone's speech can remind you of a place or a person. Even when the content is entirely new, your brain builds a map of familiarity, not by logic but by repetition and emotion. It hears what it knows, and when it doesn't know something, it guesses, it interpolates. It fills in the missing data like a painter restoring a fragment of an old fresco. This is not a flaw in your biology, it's a feature. Without this mechanism, you'd be overwhelmed by every raw sound wave hitting your eardrum, with no hierarchy, no significance, no narrative. But with memory, your brain knows what to prioritize. It recognizes your name being said across a noisy room. It filters out the hum of the refrigerator, but highlights the beep of the oven. It even anticipates the cadence of someone you love when they're about to speak, which is why mishearing a familiar voice can feel so jarring. Your memory expected something different. And here is the curious part. The more emotionally charged a sound memory is, the more dominant it becomes in shaping future perception. In one study, researchers found that patients who had undergone traumatic events processed certain neutral sounds, like footsteps or keys, jingling, with heightened amygdala activity, meaning their brains recalled emotional context where none existed. They weren't imagining the sound, but they were reliving the memory through the sound. And this effect isn't exclusive to trauma. Joy works the same way. the sound of your child's laugh, the click of a turning key when someone you love comes home, the rustle of a gift being unwrapped. These sounds become so strongly encoded that they override competing noises, taking center stage in your consciousness. In essence, your brain uses memory as an equal partner to reality when deciding what you hear. And this has fascinating consequences for perception, for music, for language, even for how we connect to each other. When you speak to someone you love, their voice is more than just syllables. It's a collage of every past moment you've shared. The tone, the pacing, the little hesitations, all of it filtered through your emotional history. That's why misunderstandings can arise, even when the words are clear, because you're not just hearing what was said, you're hearing what you remember the meaning, and the two don't always align. Our hearing is subjective, not because our ears fail, but because our memories are always involved. And even silence is not neutral. In moments of grief, silence shouts. In moments of peace, it sings. The sound of memory is not just a metaphor, it's a physical, neurological process. And in a way, this makes every sound you hear not just a reflection of the world, but a reflection of who you are. Because what your brain lets you hear, what it fills in, what it highlights, what it ignores, is shaped not just by biology, but by emotion, by attachment, by experience. Your ears might be the portals, but it is memory that gives the world its melody. And when you close your eyes tonight and think of the sounds that stay with you, the music, the voices, the rain on windows long ago, you'll realize that your mind has been composing its own soundtrack all along. One that plays even in silence, one that whispers even when the world is still, one that belongs to no one else but you. Because you don't just hear with your ears, you hear with your life. Vision happens more in the brain than the eye. You probably believe you see with your eyes, that the world around you, in all its color and detail, enters through these twin lenses and gets transmitted to your brain like a perfect camera feed. But the truth is far stranger. You don't see the world as it is. You see what your brain guesses it to be, and this guesswork accounts for far more of your visual experience than the raw data your eyes provide. Vision is often described as the dominant human sense, yet less than 10% of your brain's visual activity is driven directly by what the eyes are actually perceiving in any given moment. The rest is memory, expectation, prediction, and interpretation. In fact, your eyes capture only a small sliver of the environment with any clarity, a narrow cone of detail surrounded by a vast blur of low resolution, light, and motion. And yet, you perceive a vivid, seamless panorama, an entire world stitched together effortlessly. That's not because your eyes are powerful, but because your brain is filling in the blanks. What you see is more hallucination than observation. Your brain builds a mental model of the world and updates it only as needed. The visual cortex is a master of illusion, constantly patching, blending, inferring, and anticipating what's around you so you don't have to process every photon consciously. In experiments where visual input is manipulated, such as when participants are shown subtly distorted environments or interrupted images, the brain doesn't always notice because it assumes stability. It smooths over inconsistencies. It invents continuity. This is why you don't see the saccades. Those rapid jumps your eyes make several times, per second, as they scan your surroundings. Your brain edits them out. It fills the visual gap with guesses, like an editor removing film cuts, to maintain the illusion of a continuous take. You never see the raw footage. You see the finished movie. And in this movie, objects don't appear and disappear randomly. They persist in space because your brain assumes they should. Even when an object briefly disappears from view, your mind holds its position in memory, updating it only if something major changes. This phenomenon, called object permanence, is not innate. It's learned, and it becomes the foundation of your ability to believe in a stable, coherent world. But coherence is not reality. It's a construction. Take, for example, the phenomenon of change blindness. When significant changes to a visual scene go unnoticed, if they occur during a brief visual disruption, you might not notice that a building has changed color or that a person's clothes have altered. If the change is timed during a blink or a cut in attention. Why? Because your brain doesn't refresh the entire scene continuously. It assumes it's mostly unchanged, unless proven otherwise. That's an efficiency trick, but it also means your visual world is partially fabricated. The vivid colors you see, your brain enhances them, computed through internal algorithms based on prior experience and guesswork. Your eyes don't even detect color in the periphery, yet you believe you see a richly colored world in all directions. That belief is a cognitive illusion. Color itself doesn't exist outside your brain. It is not a property of light. It is a sensation created when photons of certain wavelengths strike retinal cells and trigger specific neural patterns, which your brain interprets as hue. The red of a rose or the blue of the sky is not out there. It's in here, inside your perception. Different cultures even divide color space differently. Some languages have no word for blue. Some people see hundreds more shades of green than others. Tetrachromats, those rare individuals with 4 types of cone cells instead of 3, see a world of color that others cannot imagine. Their vision, literally, is a different reality. And what about illusions? Optical illusions don't trick the eyes. They expose how your brain processes sight. They reveal the shortcuts and assumptions built into your visual system. Consider the Knizia triangle, where you perceive a white triangle that doesn't exist, or the Lear illusion, where 2 lines of the same length appear different. These aren't errors in your eyes. They are strategies your brain uses to interpret ambiguous input vision. Then is a conversation between sensation and simulation. Your retina sends signals, yes, but those signals are like clues, not commands. The visual cortex, especially in the occipital lobe, integrates those clues with memory, context, and probability to construct what you believe is real. And it doesn't stop there. Feedback loops from higher order brain regions like the prefrontal cortex actually shape early visual processing, sending signals backward along the neural hierarchy. This means what you expect to see changes what you actually perceive. If you're afraid, you may see shadows move. If you're hungry, food signs seem to pop out more vividly. If you believe someone is angry, neutral faces may look threatening. Your brain doesn't just see, it interprets. And its interpretations are deeply biased by your needs, beliefs, and emotions. This is not a defect, it's an adaptation in an uncertain world. Guessing is faster than waiting for clarity. Seeing, in the brain, is fundamentally probabilistic. It's not a camera. It's a story generator, and in rare cases, this generator can go rogue. In Charles Bonnet syndrome, people who have lost vision begin seeing vivid hallucinations, people, landscapes, animals. Not because they're mentally ill, but because the brain, deprived of input, begins filling the void with memory-based projections. Even in the absence of light, the brain still wants to see, and it will invent whatever it must to maintain the continuity of experience. But you don't need a syndrome to experience visual fabrication. Every dream you've had, every face you've imagined, every mental image you've summoned, these are all visual phenomena without optical input. They feel real because they are real to the brain. There is no fundamental boundary between imagined vision and perceived vision. Only the source of the signal changes. This means the mind's eye is not a metaphor, it's a system. And in some people, it's vivid enough to blur reality itself. So what does this mean for your everyday experience? It means that what you see is not what exists, but what your brain decides is useful. That's why 2 people can witness the same event and describe it differently. That's why memories morph. Because the brain reconstructs scenes each time they're recalled, based on current context. Vision is not a window, it's a canvas. And the brush is held by neurons, shaped by emotion, primed by culture, and lit by belief. You are not a passive viewer of the world, you are its active author. The world you think you see is not the raw truth. It's a brain-generated simulation that updates itself just enough to convince you of stability. You don't live in a photograph, you live in a rendering, and every blink, every glance, every flicker of attention is another brushstroke in the portrait your mind is painting. You see not just with your eyes, but with your history, your hopes, your fears, and your inner world. So the next time you look at something, really look, ask yourself, how much of this is real, and how much is me? Because vision, more than any other sense, is not just about the world outside. It's about the universe inside. Your sense of time comes from the senses. You probably think time is something you keep track of with clocks. That seconds tick forward independently of how you feel them. That there's a standard rhythm to the universe that your brain simply syncs with like a metronome. But that illusion collapses when you realize your perception of time is not controlled by a ticking mechanism, but by a fragile, invisible web spun between your senses, your eyes, ears, skin, muscles, and even your internal organs, all whispering different tempos into your brain, which desperately tries to stitch them together into a coherent flow that feels linear and continuous, even when it's anything but. Time, as you live it, is not a physical dimension. It's a constructed experience, one rooted entirely in sensory input and its interpretation. Strip away your vision, and the seconds stretch. Remove sound and minutes blur. Speed up your heartbeat and time races. Slow down your movement and the day drips like molasses. There is no central timekeeper in your body. What you call the present is an emergent illusion, an average, a best guess, a harmony born from noise. Your sense of time is not stored in a single region of the brain, but distributed across circuits that handle everything from touch to movement, from expectation to memory. And those systems are deeply flawed, wildly flexible, and shockingly easy to manipulate. Time speeds up when you're having fun because your brain processes fewer novel details, relying on routines and expectations to fill in the blanks. But time slows down during trauma, not because the moment is longer, but because your brain captures more sensory detail under stress, recording so much more per second, that when you look back on it, it feels like it lasted forever. And that feeling is what you call memory. Your memory is not a tape recorder. It's a time sculptor. It edits, compresses, stretches, and distorts, based on the emotional weight and sensory richness of the experience. That's why you can remember a childhood summer as endless, while last week vanished without a trace. But these distortions don't just happen in hindsight, they happen in real time. If you sit in silence, staring at a blank wall, with no sensory changes, time becomes unbearable, because your brain has no input to measure it by. This is why sensory deprivation chambers often make people hallucinate and lose track of time entirely. Your brain doesn't measure seconds directly, it measures change, and that change comes from the senses. Vision, for instance, plays a crucial role. The rate at which your eyes detect motion or transition helps set your internal tempo. This is why time can feel faster in the dark. Your visual system is contributing less. Similarly, your vestibular system, located in your inner ear, tracks motion and balance. And when disrupted, as in vertigo or during spaceflight, people lose all sense of temporal flow. Even your heartbeat and breath modulate your perception of time. Faster heartbeats correlate with a faster sense of time, while slow, deep breathing can make moments stretch out. Athletes and martial artists exploit this by entering flow states, where high sensory input paradoxically leads to a feeling of slowed time, allowing for faster reaction despite objective speed. This is not magic, it's multisensory integration. Your brain builds time from fragments, footsteps echoing in a hallway, lights flickering overhead, the sound of your voice delayed slightly in a cave. It compares, calibrates, synchronizes. But these processes are imperfect. In fact, they can conflict. One famous illusion, the sound-induced flash illusion, demonstrates that a single visual flash paired with two rapid beeps is often perceived as two flashes. Your auditory system, is overriding your visual one, changing not just what you hear, but what you see. And with that change, your perception of timing shifts. Your senses don't just influence your experience of time, they create it. Without them, there is no now. Patients with damage to the cerebellum, a region involved in movement and timing, often lose their ability to judge duration accurately. People with certain neurological disorders perceive time as either painfully slow or frighteningly fast. And in schizophrenia, it's common for sensory signals to become desynchronized, sound arriving late relative to vision, or movement feeling disconnected from its cause, leading to a fractured experience of time itself. Even in healthy individuals, time perception can be altered through temperature, light, motion, and sound. A cold room can feel longer. A loud ticking clock can speed up stress. Music, especially rhythm and tempo, directly shapes your temporal flow. A fast beat makes time feel shorter. A droning ambient sound can make minutes crawl. This is not metaphor, it's biology. Sensory input provides the scaffolding on which your perception of time is built. When that input changes, so does the passage of time. And this leads to a remarkable realization. Time, as you experience it, is not external. It is not a backdrop. It is not flowing like a river outside of you. It is constructed inside you, moment by moment, by the collision of light, sound, touch, emotion, and memory. There is no objective second without a subjective sense. Clocks measure cycles, not consciousness. What feels like an hour to you may feel like a second to someone else. And both are real. This has profound implications for how we live, how we age, how we remember. Children, exposed to constant novelty, build denser memories, and thus feel that time is slow and rich. Adults, bound by routine, encode less sensory data, and so the years collapse into a blur. But you can reclaim your time. You can slow it down, not by changing the clock, but by changing your attention. Engage your senses. Notice the warmth of the sun on your face, the texture of a wall, the subtle shift in a friend's voice. These are the materials of time, and just like an artist working with clay, you can shape them into something meaningful. Because time is not what happens to you. Time is what you make of what happens. And the raw material, the rhythm, the pulse, the beat, is born not in the stars or the Earth's rotation, but in the flicker of your senses, constantly translating the external world into an internal story. So when you next look at a clock and feel it lie to you, either too fast or too slow, remember this: your sense of time was never mechanical. It was always sensory, and it was always yours to rewrite. Taste is 80% smell. You probably think you know what flavor is, that it is some combination of sweet, salty, sour, bitter, maybe umami, rolling around on your tongue, delivered by your taste buds like musical notes in a familiar song. But what if I told you that most of what you think you are tasting isn't happening on your tongue at all, but in your nose? That every delicious meal you've ever had, every nostalgic bite of a childhood dish, every sip of wine or coffee or soup that stirred your soul was actually dominated, quietly but powerfully, by scent, not taste. It might sound like an exaggeration, but it is a deeply grounded scientific truth. Taste, as most people perceive it, is about 80% smell. Your tongue is a blunt tool. It can only detect 5 basic signals: sweet, salty, sour, bitter, and umami. That is it. That's all the tongue does. It's your nose, and more precisely, your olfactory system, that paints in the details, that infuses your perception of flavor with nuance, memory, emotion, and distinction. When you chew, volatile aroma molecules are released and travel up into the back of your nasal cavity through a process called retronasal olfaction, not through the front of the nose, as in sniffing, but from inside the mouth, and it's this retronasal airflow that carries the taste you think you're experiencing. This is why, when your nose is congested, everything tastes dull and flat. It's not just an inconvenience, It's a neurological disconnection between two systems that are designed to work as one. And what's astonishing is how few people realize that flavor is a multi-sensory illusion, an orchestra of smell, touch, texture, temperature, and expectation, with taste being only one small instrument in the ensemble. The mechanics of how this illusion works are intricate and beautiful. Your olfactory epithelium, a small patch of tissue in the upper part of your nasal cavity, contains millions of olfactory receptors, each tuned to detect specific molecular features. These receptors send signals directly to the olfactory bulb, which is part of your limbic system, the emotional and memory centers of your brain. Unlike sight or sound, which pass through a relay station called the thalamus before being interpreted, smell bypasses this gate and takes a direct route into your brain's emotional core. That's why the smell of cinnamon can bring you back to your grandmother's kitchen, or why the scent of a certain cologne can make your heart race or ache. The signal doesn't stop for logic or translation. It doesn't ask for permission. It arrives fully formed, infused with emotion and context. This is why, when combined with even the simplest tastes, the emotional resonance of food is amplified exponentially. A spoonful of vanilla ice cream isn't just sweet. It is smooth, cold, creamy, and wrapped in a bouquet of volatile compounds that your nose interprets as floral, caramelized, nostalgic, and your brain merges it all into a single perception, flavor. But here's where it becomes even more fascinating. Your sense of smell, and therefore your experience of taste, is incredibly subjective. There is no universal flavor of strawberry, or coffee, or cheddar cheese. What you taste is filtered through a personal history of olfactory memories, cultural experiences, genetic variation, and even mood. People have different sets of olfactory receptors, up to 30% variation from one individual to another, which means that no two people experience the same food the same way. One person may find cilantro refreshing, another may find it soapy and repulsive, all due to genetic differences in a single olfactory gene. This isn't just about preference, it's about biology, how your unique sensory wiring literally shapes your reality. And because flavor perception is primarily constructed in the brain's orbitofrontal cortex, the region where smell, taste, touch, temperature, and expectation integrate, even external factors like lighting, background noise, or the color of a plate can subtly but powerfully alter what you taste. That's why food eaten on an airplane, under low pressure, high noise, and dry air conditions, tastes bland even when it's seasoned identically to food on the ground. That's also why chefs meticulously plate dishes, pipe ambient scents into restaurants, and even adjust music, all to manipulate how your brain will interpret the flavors. The emotional weight of this cannot be overstated. Because flavor is so tightly intertwined with memory and emotion, eating becomes one of the most profound sensory experiences of being human. In studies of patients with anosmia, the loss of the sense of smell, people often report not just that food tastes dull, but that life feels empty. They describe depression, disconnection, a lack of joy, not because they miss the sensation of eating, but because they miss the emotional coloring that smell brings to every bite. These emotional links form early. Babies, even in utero, are exposed to flavor compounds through amniotic fluid, and later through breast milk. Infants whose mothers ate garlic, vanilla, or anise during pregnancy show a measurable preference for those flavors later in life. This early exposure primes the brain's flavor, emotion circuits, setting the stage for lifelong taste preferences, and further proving that taste is really smell, wrapped in memory, shaped by experience, and flavored by emotion. And the implications go beyond pleasure. Your olfactory system plays a role in appetite regulation, satiety, and even digestion. The aroma of food can stimulate gastric secretions, increase saliva, and prepare your body for eating before a single bite is taken. This is why just smelling food can make your stomach growl. On the other hand, prolonged exposure to certain smells can lead to sensory adaptation, reducing appetite or interest in eating. a phenomenon used in experimental treatments for weight control. Moreover, neurogastronomy, a field that blends neuroscience, psychology, and culinary arts, has shown that enhancing smell can improve the quality of life in people with eating disorders, depression, or neurodegenerative diseases. In one study, patients with Alzheimer's showed improved food intake and mood when exposed to strong aromatic stimuli. In another, individuals with anosmia were taught to rebuild scent recognition through olfactory training, repeated exposure to essential oils, and many regained partial flavor perception over time. This tells us that while smell is fragile, it is also plastic. It can be strengthened, retrained, and reawakened. But here's a subtle irony. We often ignore our sense of smell. We treat it as secondary, even disposable. People will protect their eyesight with glasses, their hearing with earplugs, but rarely think to protect or train their olfactory sense. Yet it is arguably the most emotionally powerful of all. Your ability to enjoy food, connect to memory, recognize danger like smoke or gas, detect disease like spoiled meat or infected wounds, or even sense pheromonal signals from other humans, all depend on a sensory system you barely think about. And it's constantly at work. Unlike sight or hearing, which can be consciously blocked by closing your eyes or plugging your ears, smell never shuts off. You are always smelling. Your brain is always sampling the air, registering changes in chemical composition, and filing them under emotional and survival relevant categories, even while you sleep. So what does this mean for how we live? It means that flavor is not a simple biological function, but a layered, deeply personal experience. One that links body and mind, perception and emotion, memory and identity. It means that eating is not just about sustenance, but about connection to your past, to your culture, to your loved ones. The soup your mother made when you were sick, the bread from a childhood bakery, the fruit you shared with someone you miss. These are not just meals. They are emotional time capsules, stored in the brain as flavor, retrievable with a single sniff. And when we say that taste is 80% smell, we're not just stating a scientific fact. We're pointing to a truth about how the brain constructs experience. How what you think you know is often an illusion crafted by invisible signals, processed outside your awareness, delivered straight to the core of who you are. So next time you eat, pay attention to your nose. Notice how aromas shift as the food enters your mouth, how they intensify or mellow with temperature, how your perception of taste changes when you breathe out. Try holding your nose while you chew, then releasing it. Feel how the world of flavor floods back in. Realize that what you're enjoying is not just food, but the seamless collaboration of multiple senses, orchestrated by a brain that never stops weaving your life into sensation. Because taste, it turns out, is not just a chemical interaction on your tongue, it's a symphony, and your nose is the conductor. Without it, the music fades. With it, every bite becomes a story, every scent, a memory, and every meal, a multi-sensory conversation between your biology and your soul. Loud sounds affect taste sensitivity. You've probably blamed a bland meal on bad seasoning, a tired chef, or maybe just your own palate having an off day. But what if the real reason that chocolate tasted dull, or that coffee felt lifeless, had nothing to do with your tongue or the food at all, and everything to do with what you were hearing in that moment? Not the words, not the conversation, but the noise. The hum of an airplane cabin, the roar of city traffic, the blaring beat of restaurant music playing just a little too loud. It might sound strange at first, but growing research in the fields of neurogastronomy and sensory integration reveals something both counterintuitive and profound. Sound, especially loud ambient sound, directly alters how you perceive taste. This isn't just a quirk of perception. It's a measurable neurocognitive effect that reshapes your experience of flavor on a fundamental level. Scientists have found that exposure to loud noise can blunt your sensitivity to sweet and salty flavors, make bitterness more tolerable, and even enhance the perception of umami, the savory, mouth-filling richness often associated with mushrooms, soy sauce, or aged cheese. This means that the flavor of your food isn't fixed. It's fluid, and it is being continuously rewritten, not just by your expectations or your memories, but by the acoustic environment around you, even if you're not aware of it. And the reason this happens has everything to do with how your brain processes multisensory information. Taste, contrary to what we were taught in childhood, is not confined to the tongue. It's a collaborative construction that takes input from smell, texture, temperature, sight, and yes, sound, and integrates it in the orbitofrontal cortex, a brain region responsible for forming the overall perception of flavor. Loud environments, especially those filled with non-specific white noise or mechanical droning, increase cognitive load, forcing the brain to prioritize survival, relevant stimuli, like keeping track of your surroundings, over subtler pleasures like taste. This reallocation of mental resources has a cost. Flavors that require nuance like sweetness or subtle herbs are the first to fade into the background, while bolder, savory elements may cut through. That's why airline food is notoriously bland. Not because of the altitude, but because of the engine noise, which can reach upwards of 85 decibels, enough to significantly dampen the flavor experience. In controlled lab settings, people eating the same food in silence and in noise report dramatically different flavor profiles, even when the food is chemically identical. Some airlines have even begun experimenting with tailored soundscapes, curated music that enhances umami or sweetness, to try and restore the full experience of food in flight. But this isn't limited to airplanes. Think of every time you've eaten at a loud restaurant, where the buzz and clatter seemed energetic at first, but left your meal feeling emotionally flat. The pleasure of eating, it turns out, isn't just about what's on the plate. It's about the acoustic texture of the space around you. Sound doesn't just shape emotion, it shapes flavor itself. And this relationship between sound and taste isn't just about volume. It's also about frequency, rhythm, and even pitch. Researchers have discovered a phenomenon called sonic seasoning, where high-pitched sounds tend to enhance sweetness, and low-pitched tones can amplify bitterness. This has been tested in countless studies where participants ate the same food while listening to different soundtracks and reported drastically altered taste perceptions, depending on the pitch and tempo of the background audio. It turns out, your brain uses cross-modal associations, neural mappings, that link unrelated senses to form judgments about taste. A bright, tinkling piano melody might make chocolate seem creamier and more indulgent, while a deep, droning bass line can make it feel darker, more bitter, or even more intense. Experimental chefs and avant-garde restaurants have begun integrating these insights into their menus, designing meals that include not just flavor pairings, but sound pairings, curating music or soundscapes that modulate the sensory experience on a subconscious level. Imagine sipping a citrusy drink while hearing crisp, high-pitched chimes and finding the acidity more exhilarating, or eating a steak to the slow pulse of a cello and feeling the umami stretch across your entire mouth. This isn't artistic fantasy, it's neuroscience in action, and it challenges our deeply held assumption that taste is somehow objective, or that your enjoyment of food is purely chemical. Your sensory reality is much more vulnerable to manipulation than you think. In fact, marketers and food scientists are already using these principles in product development, matching packaging sounds to flavor expectations. The snap of a chip bag, the fizz of a soda, the crack of chocolate breaking. These aren't just satisfying noises, they're cues that prime your brain to expect certain tastes. Alter those sounds, and your brain's prediction changes the taste itself. This is called predictive coding, a principle where your brain fills in sensory gaps based on expectation, and sound, being one of the fastest senses processed, often leads the orchestra of flavor. What's perhaps even more unsettling is how chronic exposure to certain sound environments might be slowly reshaping your sense of taste over time. If you spend most of your meals in loud cafeterias, fast food joints, or busy streets, your palate might be adapting to those conditions, requiring stronger flavors, more sugar, more salt, more fat, to reach the same levels of satisfaction. This could help explain why processed foods, which are engineered to be hyperpalatable, dominate in urban societies where eating in peace is a luxury. Over time, your brain's flavor calibration shifts, making subtle or fresh ingredients seem bland. This doesn't just have consequences for your enjoyment. It has implications for your health, your habits, and your emotional relationship with food. And it also means that restoring your ability to taste isn't just about the food itself. It may require quiet, real, intentional, restorative quiet. Not just for your ears, but for your entire nervous system. Because when the world is too loud, it's not just your hearing that suffers, it's your ability to savor life. The subtle, the nuanced, the delicate, these aspects of experience need stillness to be fully perceived. That's as true for flavor as it is for thought, emotion, or connection. And in a world increasingly saturated with noise, silence may become the rarest spice. So the next time you find yourself wondering why your favorite dish doesn't taste quite the same, don't just blame the chef or yourself. Ask what you were hearing. Notice the background hum, the crowd, the playlist, and then maybe try eating in silence, or with music that matches the flavor you want to feel. Your tongue isn't broken. Your food isn't boring. Your brain is just waiting for the right acoustic key to unlock the full spectrum of taste. Because sound isn't just something you hear. It's something you taste too. People hear the same sound differently. You might assume that when two people hear the same sound, they're having the same experience, that the sharp ring of a bell, the richness of a violin, the crackle of a fire, or the hum of an engine would register in identical ways inside different brains. But this assumption is quietly and profoundly wrong, because sound is not an objective event once it enters the body. It is a subjective construction shaped by your biology, your memory, your expectations, your language, your culture, and even your emotional state in that exact moment. The sound waves themselves may be identical, vibrating through air and into the ears of a crowd in a concert hall, or through headphones worn by millions around the world. But what happens after those vibrations touch your eardrum is a deeply personal transformation. In fact, studies in psychoacoustics and cognitive neuroscience have shown that people can interpret the same sound frequency in wildly different ways. Some will find a voice soothing, others will find it grating. Some will perceive a tone as high, pitched, others low, and even more mysteriously, some will hear words that others simply don't. This isn't imagination. It's how the brain processes auditory information. Sound doesn't exist in the brain until it is interpreted. And that interpretation isn't just influenced by your ears. It's colored by your experience, your attention, and your brain's pattern recognition systems. This is why two people can argue over whether a song lyric says green needle or brainstorm, and both can be right depending on what word they expect to hear. A phenomenon known as the McGurk effect, when applied to visual auditory integration, and broadly as perceptual priming when language and sound overlap. What you hear is partially what you predict. And this leads to a startling conclusion. Your perception of sound isn't passive. It's active, anticipatory, and deeply biased by who you are and what your brain expects reality to be. The ear is not a neutral receiver. It's a sculptor, and it's carving the world in your image. And that sculpting process begins long before you were old enough to speak. Language, for example, tunes your ears to hear certain sounds and ignore others. Not in a metaphorical sense, but literally. Infants raised in English speaking households quickly learn to distinguish between the R and L sounds. But Japanese infants, unless exposed early to English, may lose this ability because those phonemes don't function distinctly in Japanese. Conversely, tonal languages like Mandarin condition the brain to hear pitch variations as meaningful, where a rising tone may signal an entirely different word than a falling one. And this auditory sensitivity can persist across the lifespan. What you can and can't hear is shaped by the phonetic boundaries your early environment trained your brain to recognize. And this isn't just about language. Musical training has been shown to reshape auditory cortex sensitivity, allowing musicians to detect subtle variations in tone, timing, and harmonic structure that untrained ears completely miss. In MRI studies, musicians display stronger neural activation in response to the same sound stimuli compared to non-musicians, even when both groups are asked to listen attentively. In other words, two people can listen to the same note, and one hears color story and tension, while the other hears just a sound. And these differences don't only apply to trained musicians or speakers of exotic languages. Emotional state, for example, can alter the brain's auditory filters in real time. Anxiety has been shown to narrow auditory attention, making people more sensitive to high-pitched sounds or sudden changes in volume. A possible evolutionary adaptation for detecting threats. Conversely, calmness can soften the edges of sound, letting the brain blend tones more fluidly. Even hormonal fluctuations, such as those during pregnancy or in different phases of the menstrual cycle, can temporarily shift auditory sensitivity, altering how certain frequencies are processed. So when we say, we're hearing the same thing, what we often mean is, we're being exposed to the same stimulus, but what we actually hear is as unique as our fingerprints. What deepens this mystery even further is the way your brain fills in gaps in sound, not with silence, but with educated guesses. In noisy environments, your auditory system uses contextual prediction to fill in missing phonemes or notes. This is why you can understand someone speaking in a crowded room, even when parts of their sentence are masked by background noise. Your brain guesses what was said based on probability and familiarity. This predictive processing is essential for communication, but it also introduces variation. Two people may fill in the same missing syllable differently, based on what they're expecting, resulting in two distinct perceptual realities. The same mechanism explains how you can sometimes mishear song lyrics for years, only to realize later you had constructed an entirely false version based on your own assumptions. And then there's the influence of attention. If you're listening closely, you're activating entirely different neural circuits than when you're passively hearing. Focus recruits the prefrontal cortex, sharpening auditory perception, but also biasing it toward what you expect or want to hear. This is why eyewitnesses in crime cases can report hearing different phrases or tones in the same recording. And auditory hallucinations, in some psychiatric conditions, are another extreme manifestation of the same principle. The brain invents sounds that aren't there, but are so convincingly constructed that they feel completely real. All of this reinforces a staggering idea that hearing is not the passive reception of the world, but an act of creative construction. And this individual subjectivity extends into morality, politics, and empathy. Consider the tone of someone's voice during an argument. One person hears aggression, another hears passion, one hears sarcasm, another hears sincerity. The acoustic properties of the voice may be identical, but the emotional interpretation diverges, shaped by past experience, familiarity, even unconscious biases. Studies in interpersonal communication show that voice tone is more predictive of emotional impact than actual content, and misinterpretation of tone is one of the leading causes of conflict in relationships. Add cultural layers to that, and it becomes even more complex. Some cultures perceive raised voices as normal and passionate. Others perceive them as rude or hostile. The same sound again means something different to different ears. In AI research, even voice assistants have had to be programmed to adjust pitch and cadence, depending on regional expectations of politeness or clarity. Machines, in trying to replicate human speech, have inadvertently revealed how wildly inconsistent our expectations of sound really are. And if we take this one step further, into the domain of trauma, we see that sound can carry entirely different emotional weights for different people. The slamming of a door may be just a sound to one person and a source of panic to another, depending on the memories it activates. The same with a laugh, a whistle, or the sound of footsteps approaching from behind. Our auditory history is emotional history. What we hear is filtered not just through nerves and hairs and bones, but through fear, love, memory, and context. So the next time someone tells you they hear something differently, whether it's a word, a note, a tone, or a meaning, believe them. Don't assume that your version is more correct. You're not hearing the world as it is. You're hearing the world as you are. Every sound you've ever heard has rewired your auditory map, subtly altering how new sounds are processed. Your ear is a history book. Your brain is its translator. And what comes out is a deeply personal version of reality, shaped by biology, memory, attention, culture, and mood. Sound is not a shared experience. It's a mirrored one, reflecting who you are in every vibration. And maybe, just maybe, that explains why music can move one person to tears and leave another unmoved. Why one voice can feel like home and another like a threat. And why understanding one another often depends less on what's said and more on how we each uniquely hear it. You can trick one sense with another. You think you see with your eyes, hear with your ears, taste with your tongue, and touch with your skin. But what if none of those senses are as separate as you believe? And what if your brain is constantly wiring them behind your back, allowing one to influence, override, or even trick another? This isn't some abstract philosophical puzzle. It's the strange documented truth of how your perception works. The human sensory system is not a collection of isolated data channels, each confined to its own corner of the brain. Instead, it is a deeply entangled, collaborative network. And that entanglement means your senses can deceive each other in ways that feel completely real. For instance, you can hear brightness, you can feel textures with your eyes, you can taste shapes, and you can be convinced of a reality that doesn't exist simply because one sense bullies the others into agreement. This phenomenon is known as cross-modal perception, and it reveals that your brain isn't passively receiving information from the world. It's actively constructing your experience by blending different sensory inputs into a coherent story, whether that story is accurate or not. A classic example is the McGurk effect, where the same audio syllable, like bar, is perceived differently, depending on what you see a person's lips doing. If the video shows someone mouthing far, you might hear far, even though the actual sound is bar. Your ears are hearing one thing, but your eyes are editing the truth. This is not a glitch, it's a feature. Your brain prioritizes sensory integration over fidelity, and sometimes integration means fabrication. And it doesn't stop with hearing and vision. In the rubber hand illusion, for example, participants watch a fake hand being stroked while their real hand, hidden from view, is touched in perfect synchrony. After just a minute or two, their brain starts treating the rubber hand as their own, reacting with fear if it's threatened. Vision and touch have conspired to create a false body schema. In synesthesia, some people literally taste colors or see numbers as textures, a neurological cross-connection that's rare but instructive, because it hints at how flexible and manipulable your sensory boundaries truly are. But you don't have to be a synesthete to experience sensory trickery. Every person, every day, walks through a world built as much from expectation as from input. And that expectation is shaped by how your senses interpret one another. In taste, for example, you can fool your tongue with your nose, a fact already explored in detail in previous chapters. But here's where it gets deeper. You can also fool your tongue with your eyes and ears. Studies show that a strawberry-flavored drink appears sweeter when it is colored a deeper red, even if the chemical sweetness is identical. A pale pink version of the same drink may taste weaker, simply because the brain expects less flavor from a less vibrant color. In restaurants, background music affects flavor perception. Diners eating while classical music plays rate their food as more refined, more expensive, and even more delicious. Loud airplane noise, meanwhile, dulls the perception of sweet and salty tastes. a fact airlines now use to tailor in-flight meals. Even the sound of a food's crunch can alter how fresh it seems. When potato chip crunch sounds are digitally amplified, people rate them as crisper and fresher. The brain is not merely compiling sensory data, it's fusing it, weighting it, and sometimes inventing qualities based on cross-sensory agreement. If one sense leads strongly enough, the others will follow, even into fiction. This is the principle behind virtual reality immersion, augmented food experiences, and even marketing illusions. Everything from the texture of a luxury package to the pop of a champagne cork is designed to stimulate multiple senses in tandem, triggering a reaction greater than the sum of its parts. You believe what you see, sure, but you also believe what you feel, what you hear, and what you expect those things to mean. The brain's goal is not perfect representation, it's survival through efficiency. And efficiency sometimes means choosing the most plausible explanation over the most accurate one. This becomes even more apparent when we look at cross-modal correspondences, which are shared patterns in how people match sensations across senses. Most people associate high-pitched sounds with light colors and low-pitched sounds with dark ones. Pointy shapes taste sour, round shapes taste sweet, vanilla smells white, and musk smells brown. These associations are so consistent across individuals that researchers use them to study how the brain encodes meaning. In marketing, this has led to sensory branding, using shapes, sounds, textures, and colors that reinforce a product's identity through cross-sensory cues. In neuroscience, it's helped uncover how brain regions like the superior temporal sulcus and orbitofrontal cortex serve as hubs where sensory data is integrated, compared, and resolved. These hubs don't just receive input, they weigh it against memory, emotion, and attention. And because these regions are multimodal, they process input from more than one sense. They are fertile ground for sensory illusions. Consider this. When people are shown a neutral face paired with a happy voice, they perceive the face as happier than it really is. If the same face is paired with a sad voice, it suddenly looks melancholic. The emotional tone of a sound can change what you see, just as the color of a light can change what you feel in a room. And if this seems odd, consider how filmmakers rely on it constantly. Horror movies use sound design to make innocuous images terrifying, while romantic films use music to make silence feel intimate. Your brain doesn't just receive reality, it scores it like a film. So what does this mean for your experience of the world? It means that reality is negotiated, not delivered, that your understanding of what's happening at any given moment is the product of a fast, subconscious conference between your senses, with each one lobbying the brain for dominance. Sometimes vision wins, sometimes sound, sometimes expectation, and occasionally, one sense drags the others into a hallucination. This insight reshapes how we think about eyewitness testimony, taste tests, consumer behavior, and even memory formation. It also explains why people can experience the same event differently, not just emotionally, but sensorially. Two people walking through the same space may feel it differently because their brains are weighting the sensory inputs differently. And if one person's attention is drawn to sound, while the other focuses on scent, they may literally be constructing different experiences of the same moment. The consequences are profound. It means empathy requires more than imagining what someone feels. It requires imagining how they sense. It means memory isn't a camera roll, but a sensory remix that shifts over time. And it means your confidence in what you experienced is not proof of accuracy, only of internal consistency. In the end, this isn't a flaw in your system, it's a feature of your mind's incredible flexibility. The ability to cross wired senses gives you not only greater adaptability, but also deeper beauty, because it means your brain is capable of translating a smell into a feeling, a touch into a vision, a sound into a shape. Art, music, cuisine, architecture, all become richer because your senses are collaborators, not competitors. So the next time you marvel at how a song gives you chills, or how the color of a dish makes it taste better, or how the light in a room makes silence feel heavier. Pause and remember, your senses are not reporting the world. They are co-authoring it. You are not a passive observer. You are a synesthetic creator, and every moment you live is not simply perceived, but composed. One sensation tricking, guiding, and completing another in an endless ballet of meaning.